Before we start, I just want you to take a moment. Let your shoulders drop away from your ears. Let your jaw unclench. If you're lying down, let the bed or the sofa take all of your weight, because you don't need to hold yourself up right now. You don't need to hold on to anything at all. If the room is bright, you can close your eyes. If you're comfortable enough to sleep, then that's exactly what you should do. This is going to be a very slow walk through the human body, and you are welcome to drift in and out of it as you go. You won't miss anything, because we will come back to the same ideas over and over again, from different angles in different words. There's nothing to catch, nothing to keep up with, and nothing to remember in the morning. One small thing before we wander into the subject. This is made for rest and for gentle learning. It isn't professional advice of any kind, medical or otherwise, so please don't lean on it for anything that matters. And please don't listen to this while you're driving, or while you're doing anything that needs your attention. Find somewhere safe. Somewhere you can stop moving for a while. And if you'd like to come back to any of this while you're awake, the No Fluff Anatomy and Physiology Guide is linked in the description, and it covers the same ground in a form you can actually read. But you don't need it tonight. Tonight you can just listen, or not listen, or fall asleep halfway through a sentence. That's exactly what this is for. So let's start with something very small, smaller than a grain of sand, smaller than the dot at the end of this sentence, if you could see a written sentence in the dark, which you can't, and that's fine. Let's start with the cell, because every single part of you is made of cells. Your skin is made of cells, your blood is full of cells, your bones are cells too. Though they're surrounded by a hard material, those cells build around themselves, the way a snail builds a shell around its own soft body. A cell is the smallest unit of you that is still alive. It's a tiny bag of fluid, mostly water, with a thin skin around it called a membrane. The membrane isn't a solid wall. It's more like a very thin film of oil on the surface of water, something that holds together but can also flex and ripple and let certain things through. Inside the cell, there's a rounder, denser part called the nucleus, and you can think of the nucleus as the office where the instructions are kept. The instructions are written in a long, coiled molecule called DNA, and those instructions are what tell a cell what kind of cell to be. A skin cell has the same instructions as a nerve cell, but it only reads the chapters about being skin. A nerve cell only reads the chapters about being nerve. Same book, different pages. That's one of the quietest and strangest facts about the body. Every cell in you carries the whole story of you, and yet every cell only tells one small part of it. And when a lot of cells of the same kind gather together and do the same job, we call that a tissue. A tissue is a fabric. That's actually what the word means in older languages, a fabric woven from cells. There's muscle tissue, which is made of long cells that can shorten themselves and pull. There's nerve tissue, made of cells that can carry tiny electrical signals from one place to another. There's connective tissue, which is a big, quiet family of tissues that hold things together. Ligaments are connective tissue. Tendons are connective tissue. Cartilage is connective tissue. Cartilage is connective tissue. And bone is a special kind of connective tissue too, one that has been reinforced with minerals until it's hard enough to hold you upright against the pull of gravity. There's also epithelial tissue, which is the tissue that covers surfaces. The lining of your mouth is epithelial tissue. The surface of your skin is epithelial tissue. The inside of your stomach is epithelial tissue. It's the body's wrapping paper, in a sense, the layer that separates inside from outside. Now, when different kinds of tissues work together to do a particular job, that's an organ. An organ isn't one thing, it's a team. The stomach is an organ, and it's made of epithelial tissue on the inside to handle the acid, and smooth muscle tissue in the middle to churn the food, and connective tissue on the outside to hold its shape, and nerve tissue running through it to tell the muscle when to squeeze. All of those tissues, folded and layered and working together, make something new. The stomach isn't just a bag. It's a small, soft machine. The heart is an organ too, and so is the liver, and so is the skin, which surprises people sometimes. The skin is the largest organ in the body. It's a single continuous organ that covers all of you, keeping the outside out and the inside in, and it's made of all four tissue types working together. So an organ is already a collaboration. And then, when several organs work together to achieve something even bigger, we call that a system. The digestive system is a long, winding team of organs, from the mouth down to the intestines, and all of them share one job, which is to take food apart and bring the useful bits inside. The nervous system is the brain and the spinal cord, and all the long, thin nerves that reach out to every corner of you, and its job is to send signals around the body, fast. The circulatory system is the heart and the blood vessels, moving blood in a loop, delivering oxygen and taking away carbon dioxide. The respiratory system is the lungs and the airways, bringing air in and letting air out. And tonight, we're going to spend a long time with the skeletal system, the bones. But before we go there, I want you to hold on to this idea of layers, because it will come back again and again. Cells make tissues, tissues make organs, organs make systems, systems make you. One idea at a time, slowly, like stacking stones. So let's think about the skeletal system as a whole, just from a distance, before we walk into it. When people say skeleton, a lot of the time they picture the thing hanging in a science classroom, the white plastic model with the dangling arms and the rattling joints. And that's a skeleton, yes. But a living skeleton is not white and dry. A living skeleton is pink and wet and busy. Bone is not stone. Bone is living tissue, with blood vessels running through it and nerve endings woven inside it, and cells that build and cells that break down, working all the time, all through your life. Even right now, while you're lying here half asleep, your bones are being remodeled. Tiny teams of cells are taking down a little bit of old bone and putting up a little bit of new bone, the way a road crew might patch a road in the middle of the night, slowly and quietly, while no one is watching. The skeleton has a few big jobs. The first one is obvious. It holds you up. Without bones, you would be a soft pile on the floor, like a tent with no poles. The bones are the frame, the scaffolding. The second job is protection. The skull wraps around the brain like a helmet. The ribs curve around the heart and lungs like a cage. The vertebrae, those stacked rings of bone in your back, wrap around the spinal cord, which is the main cable that runs from the brain down through the body. If you cup your hand around something fragile to keep it safe, you are doing with your hand what your skeleton does with your organs, all day and all night, without you ever having to think about it. The third job is movement. Bones don't move by themselves. They move because muscles pull on them. A muscle is anchored to a bone, usually by a tendon, and when the muscle shortens, the bone moves, and when the muscle lets go, the bone can move back. It's a lever system. Every time you lift a finger, a muscle in your forearm is pulling on a tendon that runs along your hand and tugs the bone in your finger. The bone is the rigid part of the lever. Without the rigidity, the pull wouldn't do anything. It would be like trying to lift a spoon with a piece of string. The fourth job is one people forget. Bones make blood. Deep inside some of your bones, in a soft, spongy center called the marrow, new blood cells are being born constantly. The red marrow, which is found in the flat bones like the hips and the sternum and the vertebrae, is where red blood cells come from. The same red blood cells that carry oxygen from your lungs to your toes are manufactured inside your bones. Your skeleton is not just a frame, it's also a factory. And the fifth job is storage. Bone is a bank for minerals, especially calcium and phosphorus. Your body needs calcium for nerves to fire and muscles to squeeze and blood to clot. And if the level of calcium in your blood dips too low, the body can withdraw some from the bones, the way you might dip into savings to cover a small, unexpected expense. And later, when calcium is plentiful again, the bones can be topped back up. So the skeleton is also a quiet warehouse, holding on to the things the rest of the body might need later. Now, a fully grown human skeleton has about 206 bones. I say about because people vary a little. Some people are born with extra small bones in their hands or feet. Some bones fuse together as a child grows, which is why a baby has more bones than an adult. A newborn baby has around 300 bones, and as the child grows, some of those bones knit together into larger single bones. The bones in a baby's skull, for example, are not fused at first. They meet at soft, flexible seams called fontanelles, and those seams allow the skull to shape itself just enough to fit through the birth canal. And then, over the first couple of years of life, the seams close up and the skull becomes one solid helmet. That's a good example of something we'll see again in this series. The body is built to change over time. It's not a statue, it's a process. The 206 bones are not scattered around randomly. They're arranged in two main groups. The first group is called the axial skeleton. Axial comes from the word axis, the line around which something turns. The axial skeleton is the body's core, the central line from the top of your head down through your spine, plus the rib cage that branches off from that line. It includes the skull, the little bones in your ears, the bone in the front of your neck called the hyoid, the vertebrae of the spine, the ribs, and the sternum, the flat bone in the middle of your chest. That's the axial skeleton. It's the part of the frame that protects the most important cargo. The brain, the spinal cord, the heart, and the lungs are all housed within the axial skeleton. If you think of the body as a castle, the axial skeleton is the keep, the inner tower where the valuables are stored. The second group is called the appendicular skeleton. Appendicular comes from the word appendage, which means something attached or hanging. The appendicular skeleton is everything else, the bones of the arms and the legs plus the girdles that attach them to the trunk. The shoulder girdle, which is made of the clavicle and the scapula, attaches the arm to the axial skeleton. The pelvic girdle, which is made of the two hip bones, attaches the leg to the axial skeleton. And from those girdles, the limb bones reach out. The humerus in the upper arm, the radius and ulna in the forearm, the bones of the wrist and hand, the femur in the thigh, the tibia and fibula in the lower leg, the bones of the ankle and foot. The appendicular skeleton is the part that allows you to reach and walk and hold and climb. It's the part of the frame that touches the world. So if you picture the skeleton as a whole, you could see a long central column, the spine, with the skull perched on top like a lamp on a post, and the rib cage wrapping forward from the upper part of that column like a basket. And then, hanging from the top of that column, two long mobile chains that end in hands. And anchored to the bottom of that column, two thick, strong pillars that end in feet. That's the whole arrangement in a glance. Column, basket, two chains, two pillars. The rest of this series will be walking through those parts one at a time, very slowly. We'll start with bone itself, with what bone tissue is made of and why it's so strong without being brittle, and then we'll move through the skeleton region by region. But before we go any further, I want to sit with this one idea for a moment, because it's the idea that everything else rests on. You are not a solid object. You are a community. Trillions of cells, arranged into tissues, arranged into organs, arranged into systems, arranged into a body that is warm and breathing and slowly falling asleep right now. And every single layer of that arrangement is alive. The bones are alive. The blood inside them is alive. The cells that build and break and rebuild the bones are alive. You are not a machine made of parts. You are a process made of smaller processes, and all of it is happening in the dark, quietly, while you rest. Let's stay with that thought for a little while. The inside of a bone is not empty, and it's not solid like rock. It's more like a honeycomb. If you took a slice through the end of a long bone, the part near the joint, you'd see a delicate lattice of thin, bony struts, and the spaces between those struts are filled with marrow. The struts are called trabeculae, and they're arranged along lines of stress, the directions the bone gets pulled and pressed in daily life. It's a bit like the way beams in an old timber roof are placed only where they're needed. The bone grows its supports exactly where the forces demand them, and because forces change, the supports change too. If you take up running, The bones in your legs will slowly lay down more bone where the impact lands. If you spend months lying in bed, the bones will slowly thin because the body decides, in its quiet, economical way, that bone tissue that isn't being used doesn't need to be maintained. The body is always asking itself what's worth keeping, and it only keeps what you use. This is one of the reasons the skeleton is such a good place to start in anatomy. It's so obviously a structure, a frame, a thing that holds shape, and yet it's also a living tissue that adapts and repairs and changes across a lifetime. A broken bone can heal, not just close over, but actually rebuild itself, the way a wall might be repaired brick by brick until you can hardly see the seam. The cells in the broken area start to make a soft, rubbery material called callus, which holds the two broken ends steady, and then that callus is slowly replaced with real bone, layer by layer, over weeks and months. And if the bone was set straight, the healed bone can end up just as strong as it was before. It's one of the few tissues in the body that heals by making more of itself, rather than by making a scar. That alone tells you bone is alive. And if we look even closer at bone tissue, we find it's made of more than one material. Bone is a composite, which just means it's made of two different materials working together. One material is flexible and tough, and the other is hard and stiff. The flexible part is a protein called collagen, the same protein that makes up tendons and ligaments and the deeper layers of skin. Collagen is the rope. The hard part is a mineral called calcium phosphate, which forms crystals that pack themselves around the collagen fibers. The mineral is the stone. Rope alone would be too floppy to stand. Stone alone would be too brittle, and it would crack under force. But rope and stone together, woven and packed into thin layers, make something strong enough to hold your weight for 80 years, and flexible enough to bend a little when you jump and land. The collagen lets the bone flex just slightly under load. The mineral stops it from flexing too far. If you boil a bone in acid, the mineral dissolves away, and what's left is pure collagen, so soft you could tie it in a knot. If you bake a bone until the collagen burns away, what's left is pure mineral, so brittle you could snap it with 2 fingers. But together, in the right proportion, they make something remarkable. And the bone tissue itself is arranged in thin layers, like the rings of a tree, around tiny channels that carry blood vessels. These layers are called lamellae, and the whole cylinder, the rings plus the central channel, is called an osteon. It looks a little like a rolled-up carpet with a drinking straw in the middle. The cells that build bone, called osteoblasts, sit on the surface of the growing bone and lay down new layers, the way a plasterer spreads plaster over a wall. And when an osteoblast gets surrounded by the very material it has made, it becomes trapped in its own work, and then it settles down into a quieter life as an osteocyte. An osteocyte is a bone cell that lives in a tiny cave in the rock, and from there it can sense pressure and stress and send messages back to the builders on the surface. And then there are the breakers, the osteoclasts, which are large cells that dissolve small patches of old bone, carving out microtunnels that the osteoblasts will later fill back in. Build, maintain, break, rebuild. It's a cycle that never stops, not even for a single night of your whole life. So when you lie down tonight and feel the weight of your own body settling into the mattress, that weight is being held by a living scaffold, by 206 bones, each one a composite of rope and stone, each one threaded with blood vessels and nerves, each one quietly rebuilding itself in the dark. And the body doesn't ask you to manage any of it. You don't have to tell the osteoblasts when to work. You don't have to remind the osteoclasts to tidy up. It's all done for you. The same way your heart beats and your lungs breathe, and your blood makes its slow loop. You are a community of processes, and right now, the kindest thing you can do for that community is simply rest and let it get on with its work. The skull, then, is the part of the skeleton that houses the brain, and it's worth pausing here, because the skull is not one bone. It looks like one bone in the same way a cathedral looks like one stone, but it's actually made of many bones, fitted together along wavy, irregular seams called sutures. The seams are wavy for the same reason a jigsaw piece has wavy edges. It increases the surface area where the bones meet, and that makes the joint stronger. There are 8 bones in the brain case, the part that wraps around the brain. The frontal bone makes the forehead. The 2 parietal bones make the top and sides. The 2 temporal bones near your temples hold the delicate structures of the inner ear. The occipital bone makes the back of the head and has a large hole in it, called the foramen magnum, through which the spinal cord passes down from the brain into the spine. The sphenoid bone sits behind the eyes like a butterfly with outstretched wings, and the ethmoid bone, tucked up behind the nose, is light and full of air spaces. That's a pattern in the skull. Many of its bones are hollowed out with air-filled cavities called sinuses, which make the skull lighter than it would be if it were solid bone, and they also give your voice a bit of resonance. When you have a cold and your voice sounds different, it's partly because those little air spaces are swollen and full of fluid, and the sound can't bounce around in the usual way. And the face is made of more bones. The 2 nasal bones make the bridge of the nose. The maxillae make the upper jaw and hold the upper teeth. The mandible makes the lower jaw, and it's the only bone in the skull that moves. The zygomatic bones make your cheekbones. The lacrimal bones, tiny and thin, sit in the inner corner of each eye socket, and they help drain tears into the nose. That's why your nose runs when you cry. The tears are not overflowing at the eye, they're actually draining down through a little pipe in the lacrimal bone. All these bones of the face and the brain case together make up the skull, and the whole structure is designed around one idea: protecting the brain. The brain case is rounded because a rounded shape spreads out force. If you knock the side of your head, the force travels around the curve instead of punching straight through. The walls are thick in some places and thin in others, and the thin places are usually covered by muscle. It's an elegant piece of engineering, and it grew itself. Below the skull is the spine, and the spine is one of the most important parts of the entire skeleton, not just because it holds you upright, but because it protects the spinal cord, the main communication cable of the body. The spine is not one long bone. It's a stack of smaller bones called vertebrae, and there are 33 of them at birth, though some of them fuse together later in life. The top 7 are the cervical vertebrae, in the neck. They're small and light, and the first 2 have special jobs. The very first cervical vertebra, called the atlas, holds the skull like a dish on the palm of a hand, and it lets you nod your head. The second, called the axis, has a small peg of bone that the atlas rotates around, and that lets you shake your head. Then there are 12 thoracic vertebrae in the chest region, and each one connects to a pair of ribs. Then 5 lumbar vertebrae in the lower back, and these are the big ones, thick and solid, because they carry the most weight. Then the sacrum, 5 fused vertebrae at the back of the pelvis, and the coccyx, the tailbone, 3 or 4 tiny fused vertebrae at the very bottom. If you run your fingers down the middle of your back, you can feel the little bumps of the vertebrae, the spinous processes, poking out under the skin. That's your axis, your central line. It's flexible enough to bend and twist, but strong enough to hold you upright, and it's built in segments, so it can flex without breaking. The discs between the vertebrae are made of tough outer rings and soft inner jelly, and they act as shock absorbers, cushioning the bones when you walk or run or sit down too quickly. The spine is the quiet central pillar of the whole body, and every other part of the skeleton hangs from it or attaches to it in some way. The rib cage attaches to the thoracic vertebrae at the back, and it curves around to the sternum at the front. There are 12 pairs of ribs. The upper 7 pairs attach directly to the sternum with strips of cartilage, and they're called true ribs. The next 3 pairs attach to the cartilage of the rib above, and they're called false ribs. The last 2 pairs don't attach at the front at all, and they're called floating ribs. The cartilage is important. It lets the rib cage flex. When you breathe in, the ribs swing up and out, and the cartilage allows that movement without the bones grinding. The rib cage protects the heart and the lungs, and it does so while still allowing the lungs to expand. It's a cage, but it's a movable cage, a cage that breathes with you. The sternum is the flat bone in the middle of the chest, and it's divided into three parts: the manubrium at the top, the body in the middle, and the xiphoid process, a little pointed bit at the bottom. If you press gently at the base of your sternum, you can feel the xiphoid process, though it's often too deep to feel clearly. The rib cage and the sternum and the thoracic vertebrae together form a protective basket around the most vital organs, and the whole structure is light but very strong. Strong enough to take a fall and protect the heart. Light enough that breathing doesn't feel like work. And then there are the shoulders and the arms. The shoulder girdle is made of two bones on each side, the clavicle and the scapula. The clavicle is the collarbone, and it's the only bone that connects the arm to the rest of the skeleton at the front. At the back, the scapula floats over the ribs, held in place by muscles. This makes the shoulder incredibly mobile. You can reach over your head, behind your back, out to the side, across your chest. No other joint in the body has that range. But the trade-off is stability. The shoulder is the most commonly dislocated joint, because it's held together mostly by muscles and ligaments rather than deep, bony sockets. The scapula is a flat, triangular bone, and it has a little shelf on its back called the acromion and a small cup called the glenoid fossa, where the humerus sits. The humerus is the bone of the upper arm, and at its top it has a round head that fits into that shallow cup, like a golf ball sitting on a tee. The upper arm bone runs down to the elbow, where it meets the two bones of the forearm, the radius and the ulna. When you turn your palm up, the radius is on the thumb side. When you turn your palm down, the radius crosses over the ulna. That crossing is what allows your forearm to rotate. The elbow is a hinge joint, which means it only bends and straightens. The wrist is made of 8 small carpal bones arranged in 2 rows, and they allow the hand to bend and flex in many directions. The palm is made of 5 metacarpal bones, and the fingers are made of 14 phalanges, 2 in the thumb and 3 in each of the other fingers. All of those small bones give the hand its fine control. The hand is not a paddle. It's a delicate instrument, and every bone in it has a job. The pelvis is the big, bowl-shaped structure that connects the legs to the spine. It's made of 2 large hip bones, which meet at the front at the pubic symphysis, and at the back they attach to the sacrum. Each hip bone is actually 3 bones that fuse together during childhood: the ilium, the ischium, and the pubis. The ilium is the wide, flaring part you can feel at the top of your hip. The ischium is the part you sit on. The pubis is the front part. The pelvis is a protective basin for the bladder and some of the reproductive organs, and it's also the anchor for the legs. It's much more stable than the shoulder and much less mobile. The hip joint is a deep ball and socket joint, where the round head of the femur sits inside a deep cup in the pelvis called the acetabulum. The femur is the longest and strongest bone in the body. It runs from the hip to the knee, and it's built to take enormous forces. When you walk, the femur carries several times your body weight with every step, and when you run, even more. It's a thick, dense, powerful bone, and it's reinforced along its length with strong ridges where muscles attach. Below the femur are the 2 bones of the lower leg, the tibia and the fibula. The tibia is the shin bone, the big weight-bearing bone at the front. The fibula is the thin bone on the outside, and it doesn't bear much weight at all, but it helps stabilize the ankle and gives muscles a place to attach. The kneecap, called the patella, sits in front of the knee joint, embedded in the tendon of the quadriceps muscle. It acts as a pulley, giving the muscle better leverage to straighten the leg. The ankle is made of 7 tarsal bones, and the largest of them is the calcaneus, the heel bone. The foot is built like a shock absorber. It has a springy arch made of the tarsal and metatarsal bones held together by ligaments, and the arch flattens slightly when you step and springs back when you lift off. The toes are made of phalanges, like the fingers, but they're shorter and stouter. The whole structure, from the pelvis down to the toes, is built for stability and weight-bearing, not for fine manipulation. The leg is a pillar, the foot is a tripod, and together they hold you up against gravity, day after day, year after year. Now, all of these bones are connected at joints, and joints are where the magic happens. Without joints, the skeleton would be a single rigid statue, and you couldn't move at all. A joint is simply the place where two or more bones meet. Some joints, like the sutures in the skull, are fixed and don't move. They're called fibrous joints, and their job is to hold things together solidly. Some joints, like the pubic symphysis or the discs between the vertebrae, allow a little movement. They're called cartilaginous joints because the bones are joined by cartilage and they act as shock absorbers. And then there are the synovial joints, the big movers. The knee, the hip, the shoulder, the elbow, the wrist. These joints have a space between the bones, a space filled with a slippery fluid called synovial fluid, which lubricates the joint the way oil lubricates an engine. The ends of the bones in a synovial joint are covered with a smooth layer of cartilage, so they glide over each other with almost no friction. The whole joint is wrapped in a capsule of tough tissue, and inside the capsule, the fluid does its quiet work. The shape of the bones at a joint determines what kind of movement is possible. A hinge joint, like the elbow, moves in one plane only, like a door. A ball and socket joint, like the hip, can move in almost any direction. A pivot joint, like the one between the atlas and axis in your neck, rotates. A saddle joint, like the one at the base of the thumb, can move back and forth and side to side, which is what allows you to oppose your thumb to your fingers, to grip. A gliding joint, like the ones between the carpal bones, allows small sliding movements, and a condyloid joint, like the knuckles, allows bending and straightening plus a little side to side. Each joint is a compromise between mobility and stability. The shoulder is very mobile and not very stable. The hip is very stable and not very mobile. The body makes these trade-offs all over the place, and each one tells you something about what that part of the body is for. And the joints are held together by ligaments. Ligaments are tough, fibrous bands that connect bone to bone. They're not elastic. They don't stretch much, and that's the point. They hold the joint in place and stop it from moving too far in any direction. Tendons, on the other hand, connect muscle to bone, and they do have a little give. When a muscle contracts, it pulls on the tendon, and the tendon pulls on the bone, and the bone moves. Ligaments are the straps. Tendons are the cables. Both are made of collagen, but they're arranged differently, and they do different jobs. And cartilage is the cushion. It covers the ends of bones, and it's smooth and slightly rubbery. It's not as hard as bone and not as soft as muscle. It's a kind of firm, flexible padding, and it absorbs shock and lets bones glide. Unlike bone, cartilage doesn't have its own blood supply, so it heals very slowly if it's damaged. It's one of the quiet sacrifices the body makes. Cartilage lasts for decades, cushioning your joints every step you take, and it does so without being constantly rebuilt the way bone is. It's more like a set of shock absorbers that are fitted once and then used for a long, long time. There's one more thing the bones are doing tonight, even as you lie still. They're storing calcium, and the calcium is moving in and out of the bones all the time. The level of calcium in your blood has to stay within a very narrow range because calcium is used for so many things. It's needed for muscle contractions, including the beating of your heart. It's needed for nerve signals. It's needed for blood clotting. And if the level in your blood drops too low, the body releases a hormone called parathyroid hormone, which tells the osteoclasts to break down a little bit of bone and release the stored calcium into the blood. If the level rises too high, another hormone called calcitonin tells the osteoblasts to pull calcium out of the blood and deposit it into the bones. So the bones are not just a frame, they're a reservoir, a slow, steady bank that the body draws on and pays back into, all through the night, all through the day, without you ever feeling a thing. And this is one of the reasons why bones need to keep being used. The more you use them, the more they deposit and strengthen. The less you use them, the more they thin. The body reads pressure and stress as a signal to reinforce. It's the same principle as a tree growing thicker in response to the wind. The body doesn't ask if you want stronger bones. It simply responds to what you do. Let's return for a moment to the idea that we started with, the idea of nested layers, because the skeleton is a perfect example of it. A single bone cell, an osteocyte, sits in its little cave inside a lacuna. Millions of osteocytes are arranged into osteons, the concentric rings around blood vessels. Osteons are packed together into bone tissue, and bone tissue is shaped into each individual bone, with its own unique architecture, its own curves and ridges and hollows. Then those bones fit together at joints, held by ligaments and moved by tendons, into the skeleton. And the skeleton, in turn, works with the muscular system to produce movement, with the circulatory system to produce blood cells, with the endocrine system to manage minerals. So here we are again, at the same pattern. Smaller units, working together, make larger units, and each layer only works because the layer below it is alive and healthy. A bone is not a dead stick. It's a living community of cells woven into tissue, shaped into an organ, joined into a system. And that system is one part of a larger community, the whole body, which is itself a community of communities, all working together, all resting now, all waiting for the next breath, the next heartbeat, the next slow wave of sleep. And you don't have to keep track of any of this. You don't need to remember the names of the bones or the hormones or the cells. The names don't matter tonight. What matters is the simple, quiet fact that you are being held up by a living scaffold, and it is taking care of itself, and it will still be there in the morning, whether you remember a word of this or not. Your skull will still be sheltering your brain. Your spine will still be carrying your weight. Your femurs will still be standing in their sockets, strong enough to hold you. Your heart will still be beating inside the cage of your ribs. And your bones will have spent the night doing their slow, patient work, building and breaking and rebuilding, the same way they did last night and the night before, all the way back to the very first night of your life. So let all of that settle for a moment. Let the body lie there, held and holding. And when you're ready, let the next thing drift in, because we're going to keep walking through the skeleton, one region at a time, in the same slow way. The skull rests on top of the spine like a lamp on a post, and the weight of it is not as much as you might think. A human head weighs somewhere around 10 or 11 pounds, about the same as a large bag of flour, and most of that weight is the brain itself, soft and heavy and folded inside its bony case. The bones that wrap around it are surprisingly light. Some of them are only a few millimeters thick in places, and some of them are hollowed out with air spaces, as though the body had taken a careful look at the skull and decided to remove every bit of bone that wasn't needed for strength. The result is a structure that is both strong and light, a helmet made of living tissue, thin enough to carry all day without effort, strong enough to take a knock and protect what's inside. Let's start at the top of the skull and work our way down, because that's the way the body tends to be described, from the crown of the head towards the feet. The very top of the skull is called the vertex, and it's covered by a layer of skin and hair and a thin sheet of connective tissue, and then, beneath all that, the bone. The two parietal bones form the sides and roof of the skull. They're broad and gently curved, and they meet each other along a seam that runs from front to back down the middle of the top of the head. That seam is called the sagittal suture. It's one of the wavy lines you can feel if you press your fingertips gently against the top of your own head, though it's often hidden beneath the soft tissues of the scalp. The parietal bones also meet the frontal bone along a seam called the coronal suture, which runs from side to side across the top of the forehead, and they meet the occipital bone at the back along the lambdoid suture. These sutures are not like ordinary joints. They don't move. They're more like the seams in a piece of clothing, where two edges of fabric are sewn together so tightly that they act as one piece. In the skull, the edges of the bones are interlocked in a zigzag pattern, and that interlocking gives the joint more surface area and more grip. It's a little like the way two pieces of corrugated cardboard mesh together if you press them face to face. The wavy line is harder to pull apart than a straight one would be, And that's exactly what the skull needs. The frontal bone makes the forehead and the roof of the eye sockets. It's a single bone in adults, though it starts as two halves in a baby, and the two halves fuse together in early childhood. The frontal bone isn't just a flat plate, it has hollow spaces inside it, just above the eyes, called the frontal sinuses. These are air-filled cavities lined with a thin layer of mucous membrane, and they open into the nose. The frontal sinuses make the bone lighter, and they also play a small part in the sound of your voice. When they're blocked, the way they can be during a cold, the voice becomes flat and congested, and the forehead can feel heavy and full. Just below the frontal bone, at the top of each eye socket, there's a ridge of bone that you can feel under your eyebrows. That ridge protects the eye from blows from above, and it's one of the many places in the skull where the bone thickens for no other reason than to shield something delicate. The occipital bone is at the back of the head, and it forms the floor and back wall of the brain case. At its base there's a large round hole, the foramen magnum, which means great hole in Latin. The spinal cord passes through this hole and connects to the brainstem, which is the lowest part of the brain. If you imagine the head as a helmet, the foramen magnum is the opening in the bottom where the neck enters. Around the foramen magnum are two smooth oval bumps called occipital condyles, and these rest on the first vertebra of the spine, the atlas, like a shallow bowl resting on the palms of two hands. That's the joint that lets you nod your head. The occipital bone also has a ridge on its back surface where the muscles of the neck attach, and those muscles run from the base of the skull down to the spine and shoulders, holding the head upright against gravity. The two temporal bones sit on the sides of the skull, one on each side, just above and behind the ears. The temporal bones are busy bones. They house the middle and inner ear, including the tiny bones that carry sound, the malleus, incus, and stapes, which are the smallest bones in the body. The stapes, sometimes called the stirrup, is only about 3 millimeters long, about the size of a grain of rice, and it's shaped like a tiny stirrup, which is exactly what its name means. The temporal bones also contain the organs of balance, 3 little fluid-filled loops called the semicircular canals, which tell the brain which way is up. And they have a long, thin projection called the mastoid process, which sticks down behind the ear, and you can feel it as a hard bump just behind your earlobe. The mastoid process is full of air spaces in adults, and it's one of the bones that doesn't finish developing until later in childhood, which is why babies don't have that little bump behind the ear. The temporal bone also has a socket called the mandibular fossa, where the lower jaw hinges. If you put your fingertips just in front of your ears and open and close your mouth, you can feel the head of the mandible moving in that socket. That's the temporomandibular joint, the TMJ, and it's one of the busiest joints in the body. It moves every time you talk, every time you chew, every time you swallow. The sphenoid bone is one of the most difficult to picture because it sits deep in the middle of the skull, behind the eyes and the nose, and it touches almost every other bone in the brain case. It's shaped a little like a butterfly with wings spread wide. The body of the sphenoid sits in the center, and its greater wings spread out to the sides, forming part of the eye sockets and part of the temple region. It also has 2 smaller wings that project forward, and 2 thin downward projections called the pterygoid processes, which anchor muscles involved in chewing. Deep in the body of the sphenoid, there's a saddle-shaped hollow called the sella turcica, which means Turkish saddle, and it's named that because it really does look like a small riding saddle carved into the bone. The pituitary gland, a tiny but powerful endocrine gland, sits in that hollow, and the brain rests just above it. So the sphenoid is a central hidden bone, a keystone that helps hold the whole architecture of the skull together. It's one of those structures that does its work in complete silence, never seen, never felt, but essential to the shape of everything around it. The ethmoid bone is even more hidden. It sits between the eyes, behind the bridge of the nose, and it forms part of the nasal cavity and part of the floor of the brain case. It's an extremely light, delicate bone, full of air cells, and it's so thin in places that it's almost like lace. The upper part of the ethmoid has two small perforated plates called the cribriform plates, and through the tiny holes in these plates, the nerve fibers for the sense of smell pass from the roof of the nasal cavity up into the brain. If you were to hold an ethmoid bone in your hand, it would weigh almost nothing. It looks like a tiny, fragile sponge, but it does several very precise jobs. It helps form the medial walls of the eye sockets. It provides an anchor for the cartilage of the nose, and it allows the sense of smell to cross from the outside world into the brain. The smell of rain, of bread, of clean sheets, all of that enters the brain through the ethmoid bone. The facial bones are arranged below and in front of the brain case, and they form the architecture of the face. The two maxillae form the upper jaw, and they're actually fused together in the middle, forming a single upper jaw bone. The maxillae hold the upper teeth, and they also form the floor of the eye sockets and the sides of the nasal cavity. Inside each maxilla there's a large air-filled sinus, the maxillary sinus, which is the largest of the sinuses. The maxillary sinuses sit in the cheek area, and they're why a sinus infection can make your cheeks ache. The zygomatic bones are the cheekbones, and they form the outer rim and lower outer wall of each eye socket. They have a broad, flat surface that gives the face its width, and they connect to the maxillae in the front and the temporal bones at the side, forming a bony arch called the zygomatic arch. If you press your fingers against the side of your face, just below the outer corner of the eye, you can feel the zygomatic bone curving back towards the ear. The lacrimal bones are tiny, thin bones in the inner wall of each eye socket, and each one has a small groove that forms part of the tear duct. The palatine bones sit at the back of the nasal cavity and form the back part of the hard palate, the roof of the mouth. The inferior nasal conchae are thin, curved bones that project into the nasal cavity, and their shape increases the surface area inside the nose, which helps warm and humidify the air you breathe. The vomer is a thin, plow-shaped bone at the lower back of the nasal septum, the dividing wall between the two sides of the nose, and the nasal bones are two small, oblong bones at the bridge of the nose, and they give the nose its shape. Most of the nose is made of cartilage, not bone, and that's why the nose is flexible and why it can bend without breaking. If you wiggle your nose between your fingers, the movement you feel is mostly cartilage, and the two small nasal bones sit just above it, at the bridge. The mandible is the lower jaw, and it's a single, U-shaped bone with a body and two upright branches called rami. At the top of each ramus there are two projections, the condylar process, which fits into the temporomandibular joint, and the coronoid process, which anchors a chewing muscle. The mandible holds the lower teeth, and it's the only bone in the skull that moves. It hinges at the two temporomandibular joints, one on each side, and it's strong enough to bite and chew food for decades, but also delicate enough to move in the fine, rapid patterns of speech. The mandible is one of the strongest bones in the face, and it's held in place by a complex set of muscles that open and close the jaw, move it side to side, and push it forward and back. When you chew, those muscles work in careful coordination, and the temporomandibular joints glide and hinge at the same time, a combination of movements that allows the lower teeth to grind against the upper teeth with remarkable efficiency. The hyoid bone is a small, U-shaped bone in the front of the neck, and it's unique in the body because it doesn't articulate with any other bone. It floats, held in place entirely by muscles and ligaments. It sits just above the thyroid cartilage, which is the bump in the neck often called the Adam's apple, and it provides an anchor for the muscles of the tongue and the floor of the mouth and the upper throat. When you swallow, the hyoid rises and then settles back. When you speak, it helps stabilize the structures that shape sound. You can feel it if you press gently at the top of your neck, just below the jaw, but it's not always easy to find, because it's small and it moves. The hyoid is one of the quietest bones in the body, barely noticed, but it's essential for swallowing and speaking, and it's a reminder that the skeleton isn't only about support and protection. Sometimes it's about giving the soft tissues a place to hold on. Now, if we move down from the skull to the spine, we come to the central axis of the body, the long, flexible column that runs from the base of the skull to the pelvis. The spine is made of 33 vertebrae stacked one on top of another, and between each pair of vertebrae there's a soft, cushioning disc. The vertebrae are separated into 5 regions: the cervical region at the top, the thoracic region in the chest, the lumbar region in the lower back, the sacrum at the back of the pelvis, and the coccyx at the very tip. Each region has a different shape because each region has a different job. The cervical vertebrae are small and light because they only have to support the head. The thoracic vertebrae are larger and more rigid because they anchor the ribs. The lumbar vertebrae are the largest because they bear the weight of the entire upper body. The sacrum and coccyx are fused together into solid masses because their job is to transfer weight to the pelvis and to provide attachment points for muscles and ligaments. The spine is not a straight column. It has gentle curves, like a soft letter S. The cervical region curves gently forward, the thoracic region curves gently backward, the lumbar region curves forward again, and the sacral region curves backward. These curves act like a spring. They absorb shock when you walk or run, and they distribute weight evenly through the column. Without the curves, the spine would be a rigid pillar, and every step would send a jolt straight up into the skull. Each vertebra has a similar basic structure. At the front, there's a solid, cylindrical block called the body, and the bodies of the vertebrae are the weight-bearing parts. They stack on top of each other, separated by the discs, and they carry the load of the body. At the back of each vertebra, there's a ring of bone called the vertebral arch, and the arch encloses a central hole. When the vertebrae stack together, those holes line up to form the spinal canal, a long, protected tunnel that houses the spinal cord. The arch also has several projections, called processes, which stick out to the sides and back. The spinous process is the one you can feel as a row of bumps down the center of your back. The transverse processes stick out to the sides, and they provide attachment points for muscles and, in the thoracic region, for the ribs. The vertebrae also have small, flat surfaces called facets, where they meet the vertebrae above and below, and these little joints, called facet joints, guide the movement of the spine and keep it stable. The whole structure is designed so that the spine can flex and rotate and twist, but only within safe limits. The facet joints and the discs and the ligaments all work together to allow a wide range of movement without letting the bones slip out of place. The intervertebral discs are among the most important structures in the spine. Each disc has a tough outer ring called the annulus fibrosus, made of many layers of fibrous tissue arranged in a crisscross pattern, like the tread of a tire, and a soft, gel-like center called the nucleus pulposus. The gel center is mostly water, and it's very good at distributing pressure. When you bend forward, the front of the disc compresses and the gel pushes backward. When you straighten up, the pressure shifts. The discs act as shock absorbers and also as spacers, keeping the vertebrae apart so the nerves can exit the spinal cord without being pinched. Over the course of a day, the discs lose a little water because of the pressure of standing and sitting, and you actually get slightly shorter by the evening. At night, when you lie down and the pressure is removed, the discs rehydrate and you regain a little height by morning. It's a tiny change, just a few millimeters, but it's a reminder that the skeleton is not a fixed object. It breathes and shifts and changes with the rhythm of the day. The spinal cord runs down through the spinal canal, and at each level of the spine, a pair of spinal nerves branches off and travels out to the body. These nerves carry signals from the brain to the muscles and organs, and they carry sensation back from the body to the brain. The spine's job is not just to hold you up, it's also to protect this vital cable. The spinal cord is delicate, soft, and essential, and the vertebral bodies and arches and discs form a segmented, flexible armor around it. The body has taken the same approach here as it did with the skull: strong outer casing, delicate inner cargo, and because the spine is segmented, it can protect the cord while still allowing movement. A single, solid rod would be strong, but it couldn't bend. A flexible tube made of many segments can do both. The ribs, as we've said, attach to the thoracic vertebrae at the back and curve around to the front of the chest. Each rib is a long, flat, curved bone, and the upper 7 pairs, the true ribs, connect to the sternum through pieces of cartilage called costal cartilage. The cartilage gives the rib cage a little spring. When you breathe in, the muscles between the ribs contract and pull the ribs upward and outward, and the cartilage flexes and allows the chest to expand. When you breathe out, the ribs settle back down. The rib cage is not just a protective cage. It's an active part of the breathing apparatus. The lower ribs are shorter and less flexible, and the floating ribs at the very bottom don't attach to the sternum at all. The rib cage as a whole has a barrel-like shape, wider from side to side than from front to back, and it encloses the heart and lungs. The spaces between the ribs are filled with muscles and connective tissue, and the whole structure is strong enough to protect the organs, yet flexible enough to expand and contract with every breath. The sternum is a flat, narrow bone in the center of the chest, and it has 3 parts. The manubrium is the top section, and it's shaped a little like a square with rounded corners. The body is the long middle section, and it's where most of the ribs attach. The xiphoid process is the small, pointed tip at the bottom, and it's often still cartilage in young people, gradually turning to bone with age. The sternum is one of the places where red marrow is found, deep inside the spongy bone, and it's an important site of blood cell production throughout life. The sternum is also a useful landmark. If you run your fingers down the middle of your chest, you can feel the top of it, the jugular notch, a small dip between the 2 ends of the clavicles, and then the flat body of the sternum below. It's one of the places where the skeleton lies close to the surface, easy to feel beneath the skin. Now we come to the shoulder girdle, the structure that attaches the arms to the axial skeleton. The shoulder girdle is made of 2 bones on each side, the clavicle and the scapula, and it's a remarkably mobile system. The clavicle is a long, slender bone with a gentle S-shaped curve, and it runs from the top of the sternum to the acromion of the scapula. It's the only bony connection between the arm and the trunk at the front of the body. At the back, the scapula floats over the ribs, held in place by muscles, so the shoulder is free to move through a wide range of positions. The clavicle acts as a strut, holding the arm away from the chest and allowing the shoulder to swing freely. If you press your fingers along the top of your chest, just below the neck, you can feel the clavicle running from the center of your chest out towards your shoulder. It's a delicate bone, and it's the most commonly fractured bone in the body because it takes the force when you fall on an outstretched hand. The force travels up through the arm and into the shoulder, and the clavicle absorbs it and sometimes gives way. But the clavicle heals well because it's well supplied with blood, and a broken collarbone is usually treated with a sling and time. The scapula is a flat, triangular bone on the back of the rib cage. It has a shallow cup on its outer edge called the glenoid fossa, where the head of the humerus sits, and it has a prominent ridge on its back called the spine of the scapula, which runs across the bone and ends in a flat projection called the acromion. The acromion is the part you can feel as the point of the shoulder, and it forms a joint with the clavicle, the acromioclavicular joint. The scapula also has a small, hook-shaped projection called the coracoid process, which points forward and provides attachment for muscles. The scapula is mostly covered by muscles on both its front and back surfaces, and these muscles are what allow it to move. The shoulder blade can slide up and down, forward and back, and rotate, and every movement of the arm involves the scapula moving along with it. When you raise your arm overhead, the humerus moves in the glenoid socket, and the scapula rotates upward at the same time, so the 2 movements combine to allow the arm to reach all the way up. This coordination between the arm bone and the shoulder blade is called scapulohumeral rhythm, and it's one of the many places in the body where multiple parts have to work together for a simple movement to happen. The humerus is the bone of the upper arm, and it's a long bone with a round head at the top that sits in the shallow glenoid socket, like a golf ball on a tee. The head is covered with smooth cartilage, and around the socket there's a rim of fibrous tissue called the labrum, which deepens the socket a little and helps keep the head in place. Below the head, there are two bumps, the greater and lesser tubercles, where the muscles of the rotator cuff attach. The rotator cuff is a group of 4 muscles that surround the shoulder joint and hold the humerus snugly in the socket. It's the main source of stability in a joint that has very little bony stability of its own. The greater tubercle is the larger bump, facing outward, and the lesser tubercle is the smaller one, facing forward. Between them runs a groove where a tendon passes, and the whole arrangement is designed to allow a huge range of movement while still keeping the joint together. The shaft of the humerus is long and cylindrical, and partway down it there's a roughened area called the deltoid tuberosity, where the deltoid muscle attaches. The deltoid is the thick, rounded muscle that covers the shoulder, and it's the main muscle that lifts the arm out to the side. At the lower end of the humerus, the bone widens into 2 smooth, rounded surfaces, the capitulum and the trochlea, which form the hinge of the elbow. The capitulum meets the head of the radius, and the trochlea meets the ulna. The elbow is a hinge joint, and it allows the arm to bend and straighten, but not much else. The hinge shape of the bone surfaces makes the joint very stable, and it's one of the reasons the elbow is less likely to dislocate than the shoulder. The forearm has 2 bones, the radius and the ulna, and they run parallel to each other from the elbow to the wrist. The ulna is the longer of the 2 at the elbow, and it has a deep, C-shaped notch at its top, called the trochlear notch, which wraps around the trochlea of the humerus. That notch is what makes the elbow a strong hinge. At the back of the ulna there's a small, bony projection called the olecranon process, and that's the part you feel as the point of your elbow. The radius is on the thumb side of the forearm, and it's shorter at the elbow but wider at the wrist. At its top, the radius has a small, round head that fits against the capitulum of the humerus, and that head can rotate. When you turn your palm up and down, the radius pivots around the ulna. In a palm-up position, the 2 bones lie parallel. In a palm-down position, the radius crosses over the ulna, forming an X. This crossing is what allows the forearm to rotate, and it's a beautiful piece of engineering. 2 long bones, one staying still, one rolling around it, and the result is a hand that can turn a key, open a jar, hold a bowl of soup. At the wrist, the radius articulates with the carpal bones, and the ulna sits slightly back, separated from the carpals by a small disc of cartilage. The carpal bones are 8 small bones arranged in 2 rows of 4, and they're held together by many short ligaments. The bones have names that describe their shapes: the scaphoid, which means boat-shaped, the lunate, which means moon-shaped, the triquetrum, which means triangular, the pisiform, which means pea-shaped, the trapezium, the trapezoid, the capitate, which means head-shaped, and the hamate, which means hooked. The carpal bones are arranged so that the wrist can flex and extend and move side to side, and the movement is distributed across all the small joints between the bones, which makes the wrist flexible but stable. The carpal bones are also arranged into a slight arch, and over that arch runs a strong band of connective tissue called the flexor retinaculum, forming a tunnel. The tendons that bend the fingers pass through that tunnel, along with a nerve called the median nerve. If the tunnel becomes too tight, the nerve can be compressed, and that's what happens in carpal tunnel syndrome, a numbness and tingling in the thumb and first fingers. It's a reminder that the skeleton not only supports, but also shapes the spaces through which other structures pass. The palm of the hand is made of 5 metacarpal bones, 1 for each digit, and they're long bones, with a base at the wrist and a head at the knuckle. The knuckles you can see when you make a loose fist are the heads of the metacarpals, and the spaces between them are filled with muscles and connective tissue. The fingers are made of phalanges, and each finger has 3, a proximal phalanx, a middle phalanx, and a distal phalanx. The thumb has only 2, a proximal and a distal phalanx. The phalanges are small, delicate bones, but they're strong enough to withstand the everyday forces of gripping and pressing and lifting. The thumb is the most mobile of the digits because the trapezium, the The carpal bone at the base of the thumb is shaped like a saddle, and the metacarpal of the thumb sits on it like a rider on a saddle. This saddle joint allows the thumb to move in two planes, back and forth and side to side, and the combination of those movements is what allows opposition, the ability to bring the thumb across the palm to touch the tips of the other fingers. Opposition is what makes the human hand so useful, and it's the reason you can hold a pen, button a shirt, thread a needle. The thumb is a small part of the body, but its saddle joint changed what human beings could do. The pelvis is the next great structure, and it's the bridge between the spine and the legs. It's made of two hip bones, each of which is formed from three bones that fuse together during childhood. The ilium is the large, flaring upper part, and its broad surface provides attachment for the big muscles of the buttock and abdomen. The ischium is the lower, back part, and it has a thick, rounded prominence called the ischial tuberosity, which is the part you sit on. The pubis is the front part, and the two pubic bones meet in the middle at a joint called the pubic symphysis, where a disc of cartilage joins them. The two hip bones also meet the sacrum at the back, forming the sacroiliac joints, and together the two hip bones, the sacrum, and the coccyx form the bony ring of the pelvis. This ring transfers the weight of the upper body down through the sacrum and out through the two hip bones to the legs, and it also protects the organs of the lower abdomen and pelvis. The pelvis is shaped a little like a basin, with a wide top and a narrower bottom, and the shape differs between males and females. In females, the pelvis is generally wider and shallower, with a larger opening in the middle because it has to allow for childbirth. In males, it's generally narrower and deeper, with a smaller opening. These differences are subtle, and there's a lot of variation, but they're a good example of how the skeleton adapts to function. The hip joint is a ball and socket joint, and it's one of the strongest and most stable joints in the body. The ball is the head of the femur, and the socket is a deep, cup-shaped cavity in the pelvis called the acetabulum. The acetabulum is lined with smooth cartilage, and around its rim there's a ring of fibrous tissue called the labrum, which deepens the socket and improves the grip on the head of the femur. The head of the femur is round and smooth, and it's connected to the shaft by a short, angled neck. The neck is the weakest part of the femur, and it's the part that most often breaks in older people when they fall. The shaft of the femur runs down and slightly inward, so the knees are closer together than the hips, and this angle is what gives the legs their natural alignment. The shaft is thick and strong, and it has a rough ridge down the back called the linea aspera, where the big muscles of the thigh attach. At its lower end, the femur widens into two large rounded condyles, which form the upper half of the knee joint. The condyles are covered with smooth cartilage, and they rest on the flat top of the tibia, with two half-moon discs of cartilage called the menisci between them. The knee is a hinge joint, but it also allows a small amount of rotation, and the menisci act as shock absorbers and help distribute weight evenly across the joint. The patella, the kneecap, sits at the front of the knee, embedded in the tendon of the quadriceps muscle. It's a sesamoid bone, which means it's a bone that formed inside a tendon, and its job is to protect the front of the knee and to give the quadriceps muscle better leverage. The patella glides up and down in a groove on the front of the femur when the knee bends and straightens, and it's one of the few bones you can see and feel easily through the skin. Below the knee, the leg has two bones, the tibia and the fibula. The tibia is the larger, weight-bearing bone, and it runs down the front and inside of the lower leg. At its top, it has two flat plateaus that receive the condyles of the femur, and between the plateaus there's a small, rough bump called the tibial tuberosity, where the tendon of the quadriceps attaches. You can feel the tibial tuberosity as a small bump just below the front of the knee, and the front edge of the tibia runs down from it, just under the skin. That's why the shin is so easy to bump and bruise. The tibia is a thick, strong bone, and it carries nearly all the weight of the body. The fibula is a thin, slender bone on the outside of the lower leg, and it doesn't bear much weight at all. Its main jobs are to stabilize the ankle and to provide attachment for muscles. At the ankle, the fibula forms the outer bump you can feel, called the lateral malleolus, and the tibia forms the inner bump, the medial malleolus. Together they form a deep, strong socket that grips the top bone of the ankle, the talus, like a mortise grips a tenon. This ankle joint is very stable, and it allows the foot to flex and extend, and a small amount of side to side. The foot itself is made of 3 groups of bones. The tarsals, 7 bones that form the heel and the back part of the foot. The metatarsals, 5 long bones in the midfoot, and the phalanges, the bones of the toes. The largest tarsal bone is the calcaneus, the heel bone, and it's one of the strongest bones in the body because it takes the impact of every step. Above the calcaneus is the talus, and together they form the subtalar joint, which allows the foot to rock side to side and adapt to uneven ground. The other tarsal bones, the navicular, the cuboid, and the 3 cuneiforms, form the arch of the foot, and the arch is held in place by ligaments and tendons. The arch acts as a spring. When you step, the arch flattens slightly, absorbing shock, and when you push off, it springs back, returning energy. The foot is a masterpiece of adaptation, a structure that has evolved to carry the weight of a human body over miles and miles of walking, and it does so with a combination of strength and flexibility that no artificial foot has ever fully matched. So the skeleton, from the crown of the head to the tips of the toes, is a single, connected, living architecture. The skull protects the brain and the sense organs, the spine protects the spinal cord and carries the weight of the upper body. The rib cage protects the heart and lungs and breathes with them. The shoulder girdle and arms provide reach and grasp and fine manipulation. The pelvis transfers weight to the legs and protects the lower organs. The legs and feet provide support and locomotion. And every joint, every curve, every ridge and groove and hollow has a reason. The body doesn't make random shapes. Every bump is an anchor. Every hole is a passageway. Every curve is a distribution of force. And all of it, the whole 206 bones, from the tiny stapes in the ear to the long, heavy femur in the thigh, is alive. Fed by blood, sensed by nerves, rebuilt by cells, stored with minerals, responsive to use, adaptable to change. That's the skeleton. And if you are still awake through all of this, then you're doing very well, and you can let that thought carry you. But if you are drifting and the words are starting to blur into a soft stream of sound, then that's exactly where you should be. The body doesn't need you to pay attention to its bones. It's been looking after them all this time, and it will keep looking after them tonight. So let the skull rest heavy on the pillow. Let the spine soften into the mattress. Let the shoulders fall away from the ears, and the pelvis settle into its own weight, and the legs grow long and still. The skeleton is holding you, and you don't have to hold anything, and when the next part of the story begins, you can follow it or not. It doesn't matter. The bones will still be there in the morning, quietly doing their work, just as they've always done. Let's stay with the bones for a while longer, and let's go deeper into what they're actually made of, because bone is one of the most surprising materials in the body. Most people think of bone as hard and dry and dead, like a piece of chalk or a stone. And it is hard, yes. Hard enough to hold you up, hard enough to take the impact of a fall, hard enough to last a lifetime. But it's not dry, and it's not dead. Living bone is wet. It's pinkish and slightly warm, and it's threaded through with blood vessels and nerves. If you could hold a living bone in your hand, fresh from the body, it would feel heavy and cool and slightly slick, and it would bleed a little if you cut it. That's how alive it is. The hardness of bone comes not from being like rock, but from a very particular arrangement of materials, and those materials are made and maintained by living cells. It's a material built by life, not a material that life has abandoned. The two main ingredients of bone, as I've said, are collagen and mineral. Collagen is a protein, and it's the most common protein in the body. It's found in skin, in tendons, in ligaments, in cartilage, and in bone. Collagen is made of long, thin fibers, and those fibers are flexible and incredibly strong in tension, which means they resist being pulled apart. If you think of a rope, That's collagen's strength. It doesn't snap easily when you pull on it. The mineral in bone is mostly calcium phosphate, and it's arranged as tiny, flat crystals that pack themselves around and between the collagen fibers. The mineral is strong in compression, which means it resists being squashed. If you think of a stack of bricks, that's the mineral's strength. It doesn't crumble easily when you press on it. So bone is a bit like reinforced concrete. Concrete is strong in compression but weak in tension, so builders put steel rods inside it to give it tensile strength. The steel resists being pulled apart, and the concrete resists being squashed, and together they make a material that can hold up bridges and buildings. Bone does the same thing. The collagen fibers are the steel rods, flexible and strong in tension. The mineral crystals are the concrete, hard and strong in compression. Together they make a material that is tough, resilient, and very hard to break. And because the two materials are woven together at a microscopic scale, bone is much lighter than solid mineral would be, and much stiffer than collagen alone would be. It's a compromise, and the compromise works beautifully. The cells that build and maintain bone are just as important as the materials themselves. There are 3 main types of bone cells, and each one has a job. The osteoblasts are the builders. They're found on the surface of growing bone, and they produce the collagen fibers and then help deposit the mineral crystals around them. They're the ones laying down new bone, the way a bricklayer lays down bricks and mortar. Osteoblasts are busy cells, with lots of little factories inside them for making protein. They don't live forever, but while they're active, they work steadily, laying down layer after layer of new bone. And when an osteoblast has surrounded itself completely with the bone it has made, it becomes trapped in a tiny space called a lacuna, a little cave in the hard tissue. At that point, the cell changes. It becomes an osteocyte, a mature bone cell, and it settles into a quieter, longer life. Osteocytes are the caretakers. They sit in their little caves and monitor the bone around them. They can sense pressure and stress and tiny changes in the fluid around them, and they send signals to the other bone cells, telling them where to build and where to break down. They're the ones who notice when a bone is being loaded heavily and needs to be reinforced, or when it's not being used and can be trimmed back. They don't move around, but they communicate with each other through tiny channels in the bone, called canaliculi, which connect one lacuna to another. It's like a network of tunnels running through the rock, and the osteocytes reach through those tunnels with long, thin processes, touching their neighbors, passing signals along. It's a quiet, hidden communication system running through the hardest tissue in the body. The third type of bone cell is the osteoclast. The osteoclast is the demolisher. It's a large cell with multiple nuclei, and its job is to break down old or damaged bone. It does this by attaching itself to the surface of the bone and secreting acid and enzymes that dissolve the mineral and digest the collagen. The osteoclast creates a small pit in the bone, called a resorption pit, and then it moves on, leaving the pit behind for the osteoblasts to fill in later. The process of breaking down and rebuilding is called remodeling, and it's happening all the time, all through the skeleton. At any given moment, some small part of your skeleton is being dissolved and rebuilt. The osteoclasts and osteoblasts work in a coordinated rhythm, like 2 teams of road workers who never stop. The demolition team clears away the old surface, and the construction team follows behind, laying down fresh material. And because they work in small patches, the overall shape of the bone is preserved. It's not a dramatic process. It's a slow, continuous renovation going on in the dark, year after year. This is how bones repair microdamage, how they respond to new loads, and how they release calcium into the blood when the body needs it. It's a system that never sleeps, and if you look at a slice of bone under a microscope, you can see the pattern that all this activity creates. There are 2 main types of bone tissue. The first is compact bone, also called cortical bone. This is the dense, solid material that forms the outer shell of every bone. It's what you see when you look at a bare bone. Compact bone is organized into osteons, the concentric rings I mentioned earlier. Each osteon looks like a tiny cylinder, with a blood vessel running through a central channel and ring after ring of bone matrix wrapped around it. The osteocytes sit in their little caves between the rings, and their canaliculi connect them to the central channel and to each other. The whole arrangement is very orderly. It looks like the cross-section of a tree trunk, but much smaller, and repeated over and over, thousands of osteons packed together like a bundle of drinking straws. This structure makes compact bone very strong and very dense. It's the load-bearing material of the skeleton. The second type is spongy bone, also called cancellous bone. This is found inside the ends of long bones and in the middle of flat bones, like the sternum and the pelvis. Spongy bone is not dense. It's a lattice of thin, bony struts called trabeculae, arranged in a three-dimensional mesh, like the inside of a sponge or a honeycomb. The spaces between the trabeculae are filled with marrow and blood vessels. The trabeculae are not random. They're oriented along the lines of stress that the bone experiences, so the bone is reinforced exactly where it's needed and left open where it isn't. This makes spongy bone much lighter than compact bone, while still being strong enough to resist the forces that come through the ends of the bones. It's a very efficient design. The body has put dense, heavy material where the load is greatest, and light, open material where the load is less. And the result is a skeleton that is as light as it can be, while still being strong enough to do its job. The marrow inside the bones is also divided into types. Red marrow is the one that makes blood cells. It's found in the spongy bone of the flat bones, like the sternum, the ribs, the pelvis, and the ends of the long bones. Red marrow is red because it's full of blood-forming cells and a rich supply of blood vessels. It's the factory where red blood cells, white blood cells, and platelets are born. Every second, millions of new blood cells are being made in the red marrow, and they're released into the bloodstream to do their work. Yellow marrow is found in the shafts of long bones, and it's mostly fat. It's a store of energy, and it can be converted back to red marrow if the body needs to ramp up blood cell production, such as after severe bleeding. The marrow is soft and protected inside the hard shell of the bone, which is a good example of the skeleton looking after the next generation of blood cells the same way it looks after the brain and the heart. The bones are not just the frame, they're also the cradle for the blood. Blood supply to bone is another thing that surprises people. Bones are not solid blocks without circulation. They have their own arteries and veins, running through the central channels of the osteons and through the marrow spaces. A long bone typically has a main nutrient artery that enters through a small hole in the shaft, called the nutrient foramen, and then branches out through the marrow and the compact bone. The ends of the bone have their own blood supply from nearby vessels. If a bone is fractured, this blood supply is what allows it to heal, because the blood brings in the cells and the nutrients needed to build new bone. The blood supply is also why bones bleed when they break, and why a broken bone can be a serious injury. It's not just a crack in a hard material. It's a living tissue, with blood vessels running through it, and those vessels are torn when the bone breaks. But that same blood supply is what makes repair possible. The body responds to a fracture the way it responds to any other injury. It sends in the builders and the demolition crew, clears away the damaged tissue, and starts rebuilding. The healing of a bone is a slow, careful process, and it follows a pattern. First, a blood clot forms around the break. Then, cells move in and start to clear away dead tissue. Then, a soft, rubbery material called callus forms around the break, made of cartilage and fibrous tissue, holding the two ends together like a temporary splint. Then, over weeks and months, the callus is replaced with real bone, remodeled into the same shape as before, strengthened where the load demands. The body doesn't just patch the break, it rebuilds the bone from the inside out, and it can restore the bone to nearly its original strength. That's a remarkable thing for a material that's often thought of as dead. Now, if you remember the very beginning of all this, we talked about how cells make tissues, tissues make organs, and organs make systems. Bone is a perfect example of that. A single osteocyte sitting in its little cave is a cell. Thousands of osteocytes, connected by canaliculi and surrounded by mineralized collagen, form bone tissue. Bone tissue is shaped into a whole organ, a femur or a rib or a vertebra, each with its own particular architecture. And all the bones together, joined at their joints, wrapped in their membranes, fed by their vessels, form the skeletal system. And the skeletal system works with the muscular system to move, with the circulatory system to make blood, with the endocrine system to manage minerals. It's all connected. There is no part of the body that works alone. And the deeper you go into any one part, the more you find it connected to every other part. That's one of the quiet lessons of anatomy. The body is a single, continuous, living system, and the boundaries we draw between its parts are mostly there to help us think about it, not because the parts are actually separate. Let's think about the membranes that wrap the bones. Because bones are not bare inside the body. They're covered and lined. The outside of every bone is covered by a tough, fibrous membrane called the periosteum. The periosteum is rich in blood vessels and nerves, and it's the layer that hurts when you bruise a bone. It also contains a layer of cells that can become osteoblasts, so it's important for bone growth and repair. When a bone is fractured, the cells in the periosteum spring into action and start producing new bone to heal the break. The periosteum also provides attachment points for tendons and ligaments, which blend into it and anchor to the bone underneath. The inside of every bone is lined by a thinner membrane called the endosteum, which lines the marrow cavity and the spaces of spongy bone. The endosteum also contains bone-forming cells, and it's involved in remodeling and calcium regulation. So a bone is not just a lump of hard material, it's a layered structure, with a tough outer wrapping, a dense outer shell, a porous inner framework, and a soft, living marrow at the center. Each layer has its own job, and each layer depends on the others. And bones grow. They grow in length during childhood and adolescence, and they grow in width throughout life. The growth in length happens at the ends of long bones, at regions called growth plates or epiphyseal plates. These are discs of cartilage near the ends of the bones, and they're where new bone is added as a child grows. The cartilage cells divide and form new cartilage, and the new cartilage is gradually replaced by bone on the shaft side of the plate. The process continues until the growth plates close, which happens at different ages in different bones, but generally by late adolescence or early adulthood. Once the plates close, the bone can no longer grow in length. The growth in width happens through a different process. The periosteum adds new bone to the outer surface, while the endosteum removes bone from the inner surface, so the bone gets wider without becoming too heavy. This process continues throughout life, and it's how bones adapt to the loads placed on them. If you become heavier, your bones get thicker. If you become more active, your bones get denser. The skeleton is always adjusting, always responding to the life you're living. And the skeleton changes as we age. In early life, it's growing and building. In middle life, it's maintaining and remodeling. In later life, the balance can shift, and bone loss can outpace bone formation. This is especially true for women after menopause, because estrogen, a hormone that helps maintain bone density, decreases. The result can be a condition called osteoporosis, in which the bones become thinner and more fragile. It's not a dramatic process. It happens slowly, over years, often without any symptoms until a bone breaks. But the fact that it happens at all is a reminder of how dynamic bone is. It's not a fixed structure that you're given once and keep forever. It's a living tissue that changes with you, and it needs a steady supply of nutrients and activity to stay strong. Calcium and vitamin D are important, because calcium is the raw material of the mineral, and vitamin D helps the body absorb calcium from the diet. Weight-bearing activity is important too, because it tells the bones that they need to stay strong. The bones don't know anything in a conscious way, of course, but they respond to the signals they receive, and those signals come from the loads you place on them and the nutrients in your blood. So the quiet work of the skeleton is shaped by the quiet choices of the life you live. But none of that needs to be thought about tonight. Tonight, The bones are doing their work without any help from you, and that's the beauty of it. The osteoblasts and osteoclasts are going about their slow, careful renovation. The osteocytes are sitting in their caves, sensing the gentle weight of your body against the bed. The marrow is producing blood cells by the million. The periosteum is holding everything together. And you don't have to do a thing. You can lie there and let the whole system run itself, because that's what it's built to do. It's been running itself since before you were born, and it will keep running itself after you fall asleep, and it doesn't need your attention. It only needs your rest. So let's return once more to the simplest version of the idea, the version you can hold on to without effort. The bones are the frame. They hold you up. They protect the soft parts. They work with the muscles to move you. They make your blood. They store your minerals, and they're alive. Every bone is a living organ, made of living cells, fed by living blood, wrapped in living membrane, and slowly, quietly, patiently rebuilding itself all the time. That's the skeleton. Not a dry white relic in a classroom, but a warm, wet, breathing part of you. And the rest of the body is built the same way. Every organ, every tissue, every system is alive and busy and self-maintaining, and the more you learn about it, the more it looks like a quiet miracle. But for now, the only thing you need to know is this. The body is looking after itself. It doesn't need you to watch over it. It doesn't need you to stay awake. So let it work in the dark and let yourself drift. There is a long, quiet road that runs through the middle of the body, and we have walked along parts of it already. It starts at the base of the skull and runs down through the neck, through the chest, through the lower back, and into the pelvis. It is the spine, and it is worth spending a long time with, because so much of the rest of the body is arranged around it. The spine is the body's central axis, the line around which everything else is organized. It holds the head up. It carries the weight of the upper body. It protects the spinal cord. It anchors the ribs. It transfers weight to the pelvis and the legs. It bends and twists and flexes, and it does all of this without you ever having to think about it. It is one of the most beautifully engineered parts of the entire skeleton, and it is made of many small pieces fitted together, piece by piece, like a stack of coins that can move but never fall apart. Let's begin at the top of the spine, with the neck. The neck is a narrow, flexible tower of 7 vertebrae, and those 7 bones have a very big job. They hold up the head, which weighs about 10 or 11 pounds, and they do it while allowing the head to move in almost every direction. You can nod, you can shake your head, you can tilt your ear toward your shoulder, you can turn to look over your shoulder, and all of that movement comes from the 7 small bones of the cervical spine. The first 2 cervical vertebrae are so specialized that they have their own names. The first one is called the atlas, and the second is called the axis. These names come from old stories, but the bones themselves are very real, and they form a small, precise joint that gives the head its greatest range of motion. The atlas is named after the figure from myth who held up the sky, because the atlas bone holds up the skull. It is shaped like a ring, with 2 shallow cups on its upper surface where the rounded condyles of the occipital bone rest. The atlas doesn't have a body like the other vertebrae. It's mostly just a ring of bone, because its job is not to bear weight, but to cradle and allow movement. The skull sits on it like a shallow bowl on a ring, and the joint between them allows you to nod. When you slowly drop your chin toward your chest, or tilt your head back to look at the ceiling, you are moving the occipital condyles in the cups of the atlas. The axis, the second vertebra, has a small peg of bone sticking up from its body, and that peg is called the dens, or the odontoid process. The atlas sits on the axis, and the dens pokes up through the ring of the atlas, forming a pivot. When you shake your head from side to side, the atlas rotates around the dens of the axis, and the whole skull rotates with it. It's a beautifully simple mechanism, a peg and a ring, and around them, the head can turn. The remaining 5 cervical vertebrae are more ordinary in shape, but they're still small and light compared to the vertebrae lower down, because they only have to carry the weight of the head. They have small bodies, and their spinous processes are short and often split at the tip. They also have small holes in their transverse processes, called transverse foramina, and through those holes run the vertebral arteries, which carry blood up to the brain. The neck is not just a passage for the spinal cord. It's also a protected corridor for blood vessels and airways and the esophagus, all of them packed into a very small space, all of them essential, and all of them sheltered by the bones and muscles of the cervical spine. Below the neck comes the thoracic spine, and this is the region that anchors the ribs. There are 12 thoracic vertebrae, and each one has facets on its body and transverse processes where the ribs attach. The thoracic vertebrae are larger than the cervical ones because they have more weight to carry, but they're also more limited in their movement because the rib cage holds them relatively still. The upper body needs to twist and bend, but it also needs to protect the heart and lungs, and the thoracic spine balances those two needs. It allows some rotation and some side bending, but not as much as the neck or the lower back. The thoracic vertebrae also have long, downward-pointing spinous processes, which overlap each other like shingles on a roof, and that overlapping further limits movement but adds protection. If you run your fingers down the middle of your upper back, you can feel the tips of these spinous processes, especially when you bend forward. The thoracic spine is the most stable part of the spinal column, and it's the part that protects the spinal cord as it passes through the chest. Then comes the lumbar spine, the lower back, and this is where the weight-bearing gets serious. There are 5 lumbar vertebrae, and they are the largest of the movable vertebrae. Their bodies are big and thick and kidney-shaped, built to carry the weight of the entire upper body, plus whatever you're holding, plus the forces of walking and lifting and twisting. The lumbar spine is also the most mobile part of the spine after the neck, and that combination of mobility and heavy load is why the lower back is such a common site of strain and injury. The lumbar vertebrae have short, thick spinous processes that point straight back, and they have large transverse processes for the attachment of the big muscles of the back. The discs between the lumbar vertebrae are the thickest in the spine because the lower back has the most compression and the most movement to absorb. The lumbar spine curves gently inward, a shape called lordosis, and that curve helps distribute the weight of the upper body over the pelvis. When you bend forward to touch your toes, the lumbar spine flattens and flexes. When you arch your back, it extends. When you twist from side to side, it rotates. All of that movement is happening in 5 small joints, and the discs and ligaments and muscles around them are working hard to keep the movement smooth and controlled. Below the lumbar spine are the sacrum and the coccyx. The sacrum is a triangular wedge of bone at the back of the pelvis, and it's made of 5 vertebrae that fuse together during development. The sacrum sits between the 2 hip bones, and it forms the keystone of the pelvis. It transfers the weight of the spine down into the pelvis, and from there into the legs. The sacrum also contains a continuation of the spinal canal, and through it pass the nerve roots that supply the lower body. The coccyx is the tailbone, a small, curved remnant at the very bottom of the sacrum, made of 3 or 4 tiny fused vertebrae. It's the last little piece of the spine, and it's the vestige of a tail that our ancestors had long ago. It has no great function now, but it provides a small attachment point for some muscles and ligaments, and it's a reminder that the body carries its history inside it. The spine, from the atlas to the coccyx, is a long, segmented column, and every segment is shaped by its position and its job. The neck is small and mobile. The chest is stable and protective. The lower back is big and strong and flexible. The sacrum is fused and solid. The whole column is a masterclass in doing many things at once. And between every pair of movable vertebrae, there is a disc. The intervertebral discs are the soft, cushioning spacers that give the spine its spring. Each disc is made of 2 parts. The outer part is the annulus fibrosus, a tough ring of fibrous tissue arranged in layers that cross each other at angles, a little like the layers of a tire. The inner part is the nucleus pulposus, a soft, gel-like center that is mostly water. The nucleus is held in place by the annulus, and together they form a structure that can absorb compression and distribute it evenly across the body of the vertebra below. When you stand, the weight of your body compresses the discs, and the nucleus pushes outward against the annulus. When you lie down at night, the compression is removed, and the discs slowly reabsorb fluid and plump up again. That's why you're slightly taller in the morning than at night, and why astronauts in space, where there's no gravity, get a little taller as their discs expand. The discs also allow movement. When you bend forward, the front of the disc compresses, and the nucleus pushes backward. When you bend backward, the opposite happens. When you twist, the layers of the annulus tighten and resist the rotation, then spring back. The discs are not passive lumps of gristle. They're active, responsive structures that change shape and pressure with every movement you make. They have no direct blood supply in adults, so they rely on movement to pump fluid in and out and to bring in nutrients. That's one of the quiet reasons why movement is good for the spine. It keeps the discs fed and healthy. And it's why lying still for too long, or sitting in one position for hours, can make the back feel stiff. The discs are thirsty for movement, and when they don't get it, they let you know. The spinal cord itself runs down through the central canal of the vertebrae, and it's one of the most protected structures in the body. The cord is a thick bundle of nerve tissue, about the width of your little finger, and it runs from the brainstem down to about the level of the first or second lumbar vertebra, where it tapers into a thin thread. Below that level, the canal is filled with a bundle of nerve roots called the cauda equina, which means horse's tail, because that's exactly what it looks like. The spinal cord carries signals both ways. Motor signals travel down from the brain to the muscles, telling them to contract. Sensory signals travel up from the body to the brain, carrying touch and pain and temperature and position. It's a two-way cable, and it's essential for nearly everything the body does. The vertebrae, the discs, and the ligaments around them all exist to protect this cable. The bones form a hard, segmented tube. The discs cushion it from shock. The ligaments hold the segments in place. And the spinal fluid, which fills the space around the cord, acts as a further shock absorber. The cord floats in a bath of clear fluid, inside a tough membrane, inside a bony canal, and the whole arrangement is designed to keep it safe from the bumps and jolts of everyday life. Now, the ribs attach to the thoracic spine, and together the spine and ribs form the thorax, the chest. The thorax is a bony cage, and its job is to protect the heart and lungs while still allowing breathing. The 12 pairs of ribs are long, flat, curved bones, and they sweep forward from the thoracic vertebrae to the sternum. The upper 7 pairs are the true ribs, and each one has its own strip of cartilage, connecting it directly to the sternum. The next 3 pairs are the false ribs, and their cartilages join together and attach to the cartilage of the rib above. The last 2 pairs are the floating ribs, and they don't attach to the sternum at all. Their ends are free, floating in the muscles of the body wall. The ribs are not solid hoops. They're elastic, and that elasticity is what allows the chest to expand. When you breathe in, the muscles between the ribs contract and lift the ribs upward and outward, and the cartilage at the front stretches and bends. The chest cavity gets bigger, the pressure inside drops, and air flows into the lungs. When you breathe out, the ribs settle back down, the chest cavity gets smaller, and air flows out. It's a quiet, rhythmic movement, and it happens about 12 to 20 times a minute, every minute, all through the night. The rib cage is a protective vault, and a breathing bellows at the same time, and it does both jobs without a pause. The sternum, at the front of the chest, is the anchor point for most of the ribs. It's a flat, dagger-shaped bone, with the manubrium at the top, the body in the middle, and the xiphoid process at the bottom. The manubrium has a small notch at its top, the jugular notch, which you can feel in the hollow at the base of your throat. The manubrium also has 2 small sockets where the clavicles meet the sternum, and those are the only bony connections between the arms and the axial skeleton. The body of the sternum is the long, flat part, and it's where the cartilages of the true ribs attach. The xiphoid process is the small, pointed tip at the bottom, and it's made of cartilage in childhood and gradually ossifies with age. The sternum is one of the sites where red marrow is found throughout life, and it's a common site for bone marrow biopsy when doctors need to look at blood cell production. It's a quiet, essential bone, lying just under the skin in the middle of the chest, doing its work without any attention. Now, if we follow the spine down to the pelvis, we come to the place where the weight of the upper body is handed over to the legs. The pelvis is a bony ring, and it's made of 3 bones that fuse together during childhood. The 2 hip bones, one on each side, and the sacrum at the back. Each hip bone is itself made of 3 bones that fuse together even earlier: the ilium, the ischium, and the pubis. The ilium is the large, wing-like upper part, and its broad, flat surface is what you feel when you put your hands on your hips. The crest of the ilium is a thick ridge along the top, and it's an important attachment point for many muscles. The ischium is the lower back part, and it has a thick, rounded bump called the ischial tuberosity, which is the part you sit on. When you sit on a hard chair, the pressure you feel is the ischial tuberosities pressing up against the seat. The pubis is the front part, and the 2 pubic bones meet in the middle at the pubic symphysis, a joint made of cartilage that allows a tiny amount of movement. The 3 bones meet at a deep cup-shaped socket called the acetabulum, which is where the head of the femur sits. The acetabulum is one of the deepest sockets in the body, and it's deepened further by a rim of cartilage called the labrum. This deep socket makes the hip joint very stable, and it's one of the reasons the hip can bear so much weight without dislocating. The pelvis has 2 main jobs. The first is to transfer weight from the spine to the legs. When you stand, the weight of your upper body comes down through the lumbar spine, into the sacrum, and then out through the 2 hip bones to the heads of the femurs. The pelvis is a ring, and a ring is a very strong shape for distributing force. The weight doesn't travel in a straight line. It spreads out around the ring and down through both legs, and the bones of the pelvis are thickened and buttressed along the lines of force. The second job is protection. The pelvis forms a bony basin that holds and protects the bladder, the rectum, and, in women, the uterus and ovaries. These organs sit inside the pelvic cavity, surrounded by the bones of the pelvis, and the bones shield them from impact. The pelvis also provides attachment for many muscles, including the big muscles of the buttock and the muscles of the abdominal wall. It's the hub where the upper body and the lower body meet, and it's shaped by its dual role as a load-bearing structure and a protective basin. The hip joints sit on either side of the pelvis, and they're the joints where the legs attach. Each hip joint is a ball and socket joint, and it's one of the most stable joints in the body. The ball is the head of the femur, and the socket is the acetabulum. The head of the femur is smooth and round, and it's covered with cartilage that reduces friction and cushions the joint. The acetabulum is deep and cup-shaped, and it grips the head of the femur the way a socket grips a ball. Around the joint is a strong capsule of ligaments, and inside the joint there's a ligament called the ligamentum teres, which runs from the head of the femur to the floor of the socket and carries a small artery. The hip joint allows movement in all directions, but it's more limited than the shoulder, because stability is more important here than mobility. The hip can flex and extend, move out to the side and back in, and rotate inward and outward, but it can't reach behind the back or over the head the way the shoulder can. And that's the trade-off. The shoulder is built for reach and manipulation. The hip is built for bearing weight and walking. Each joint is shaped by its job, and the shapes of the bones tell you exactly what each joint is for. The femur is the long bone of the thigh, and it's the longest and strongest bone in the body. It runs from the hip to the knee, and it's built to take enormous forces. When you walk, the femur carries several times your body weight with every step. When you run or jump, it carries even more. The shaft of the femur is thick and dense, and it's slightly curved, which helps distribute stress. At its top, the femur has the round head, the short neck, and 2 large bumps, the greater and lesser trochanters, where powerful muscles attach. The greater trochanter is the large bump you can feel at the side of your hip, and it's the attachment point for the gluteal muscles. The lesser trochanter is a smaller bump on the back, and it's the attachment point for the iliopsoas, the main muscle that flexes the hip. The neck of the femur is the narrow part between the head and the shaft, and it's the weakest part of the bone. In older people, especially those with osteoporosis, the neck of the femur is a common site of fracture, and a broken hip is usually a fracture through the neck of the femur. At its lower end, the femur widens into two large, smooth condyles, one on the inside and one on the outside, and these condyles form the upper half of the knee joint. Between the condyles there's a deep notch at the back, and the kneecap glides in a groove at the front. The femur is a bone that is built to last. It's dense, it's heavy, and it's held in place by some of the largest muscles in the body. It's the central pillar of the lower body, and every step you take depends on it. The knee is the largest joint in the body, and it's a hinge joint with a little bit of rotation. It's made by the meeting of the femur above and the tibia below, with the patella at the front. The surfaces of the knee are not a perfect match, so the joint relies on two half-moon discs of cartilage, the menisci, to fill in the gaps and cushion the load. There are two menisci in each knee, a medial one on the inside and a lateral one on the outside. They're shaped like wedges, thicker on the outside edge and thinner toward the center, and they deepen the shallow sockets of the tibia, so the round condyles of the femur have a better place to rest. The menisci are made of tough fibrocartilage, and they act as shock absorbers, spreading the weight of the femur over a larger area of the tibia. They're also slightly mobile, moving a little as the knee bends and straightens, which helps the joint track smoothly. The knee is held together by strong ligaments. The cruciate ligaments are inside the joint, crossing each other like the letter X. The anterior cruciate ligament stops the tibia from sliding too far forward, and the posterior cruciate stops it from sliding too far back. The collateral ligaments are on the sides, and they stop the knee from buckling sideways. All of these ligaments, plus the muscles around the knee, keep the joint stable despite the huge forces that pass through it. The knee is a remarkable joint, but it's also vulnerable, because it sits between two long levers and bears the full weight of the body, and it has to do that while bending and straightening and twisting through every step. It's one of the most commonly injured joints in the body, and that's not surprising when you think about what it does. Below the knee, the leg has two bones. The tibia is the shin bone, and it's the large, weight-bearing bone on the inside. It runs down the front of the lower leg, just under the skin, and it's the bone you feel when you bump your shin. The top of the tibia is wide and flat, with two shallow sockets where the condyles of the femur rest, and between those sockets is a small, rough bump called the tibial tuberosity, where the patellar tendon attaches. At its lower end, the tibia forms the inner bump of the ankle, the medial malleolus, and it also has a flat surface that forms the roof of the ankle joint. The fibula is the thin, slender bone on the outside of the lower leg, and it doesn't bear much weight at all. Its top end sits just behind the knee, and its lower end forms the outer bump of the ankle, the lateral malleolus. The fibula is important because it stabilizes the ankle joint and gives muscles a place to attach, but it's not a major load-bearing bone. You can actually remove most of the shaft of the fibula, and the leg still works, because the tibia carries the weight. The two bones are connected along their length by a strong sheet of connective tissue called the interosseous membrane, which holds them together and gives them more surface area for muscle attachment. The tibia and fibula, like the radius and ulna in the forearm, are a pair of bones that work together, one carrying the load, one providing stability and muscle attachment. The ankle is a hinge joint, and it's much more stable than the wrist. The bones of the lower leg form a deep, square socket, and the top bone of the foot, the talus, fits snugly into it. The socket is called a mortise, and the shape of the talus is like a tenon, a projecting piece that fits into the mortise. The ankle allows the foot to point down and pull up, but it doesn't allow much side-to-side movement. That side-to-side movement comes mostly from the joints below the talus, the subtalar joint, and the other joints of the foot. The ankle is held together by strong ligaments on the inside and outside, and those ligaments can be sprained when the foot twists suddenly. An ankle sprain is usually a stretch or tear of the ligaments on the outside of the ankle, and it happens when the foot rolls inward, stretching those ligaments beyond their limit. The ankle is a good example of the trade-off between mobility and stability. The ankle is stable, so it's good at bearing weight and pushing off, but it's not as flexible as the wrist. The foot has its own flexibility, though, and it's found in the many small joints of the foot, rather than in the ankle itself. The foot is made of 3 groups of bones: the tarsals, the metatarsals, and the phalanges. The tarsals are 7 bones in the back part of the foot. The talus is the top bone, and it forms the ankle joint. The calcaneus is the heel bone, and it's the largest and strongest bone in the foot. The calcaneus takes the impact of every step, and it has a broad, rounded back end where the Achilles tendon attaches. The Achilles tendon is the thick, strong tendon that runs down from the calf muscles, and when those muscles contract, they pull on the calcaneus and push the foot down, which is what allows you to stand on your toes. Below the talus and the calcaneus, the other tarsal bones are the navicular, the cuboid, and the 3 cuneiforms. These bones form the arch of the foot, and the arch is one of the most important features of the whole lower body. The foot has 2 arches, a longitudinal arch that runs from the heel to the ball of the foot, and a transverse arch that runs across the middle. The arches are held up by ligaments, and they're supported by the muscles and tendons of the lower leg and foot. When you stand, the arches flatten slightly and the foot spreads. When you push off, the arches spring back, and that spring stores and releases energy with every step. The foot is a natural shock absorber, and the arches are what make it work. A flat foot, where the arch is low or absent, and a high-arched foot, where the arch is too rigid, can both lead to foot and leg problems, because the shock absorption is not working as it should. The 5 metatarsals are the long bones in the middle of the foot, and they form the ball of the foot. They're similar to the metacarpals of the hand, but they're longer and thicker, and they bear weight. The phalanges are the bones of the toes, and each toe has 3, except the big toe, which has 2, just like the thumb. The toes are shorter and less mobile than the fingers, because they don't need to grasp. Their job is to provide a stable base for standing and to help with balance and push-off. The big toe, in particular, is very important for walking because it's the last part of the foot to leave the ground with each step, and it pushes off with significant force. The whole foot, from the talus in the ankle to the tips of the toes, is a beautifully integrated structure built for the repetitive, rhythmic work of walking, and it does that work better than any machine yet made. So the lower body, from the pelvis down to the toes, is a system of load-bearing bones and stable joints, designed to support and move you. The pelvis is the hub, the femur is the pillar, the knee is the hinge, the tibia is the weight-bearer, the fibula is the stabilizer, the ankle is the mortise, and the foot is the spring. All of it works together, and all of it is held together by ligaments and moved by muscles. And at the very center of it all, connecting the upper body to the lower, is the spine. The spine that holds up the skull, anchors the ribs, transfers weight through the pelvis, and protects the spinal cord. The spine that bends and twists and flexes and springs. The spine that is made of 33 small bones and 23 discs and 100 small joints and more muscles and ligaments than anyone needs to count. The spine that is, in so many ways, the quiet center of everything. If you are lying down right now, the spine is lying with you. The curves are still there, softened by the mattress. The discs are slowly rehydrating after the day's compression. The vertebrae are resting in their stack, and the spinal cord is floating in its fluid bath, carrying no urgent messages, just the slow, gentle traffic of a body at rest. And the spine is doing exactly what it does best, which is holding you, quietly, without any fuss, while you drift. It has been doing that every night of your life, and it will do it again tonight, and you don't have to think about it at all. We have walked from the top of the skull down to the tips of the toes, and along the way we have seen how the skeleton is built from living bone, how it protects the soft parts, and how it carries weight through the spine and the pelvis and the legs. Now we can turn to something a little different. We can look at how the bones actually work with the rest of the body to make you move. Because bones by themselves don't move. They are the levers, but something has to pull them. A skeleton lying on a table is still. It only moves when muscles pull on it, and the muscles only pull when the nerves tell them to, and the nerves only carry signals when the brain or the spinal cord sends them. So movement is not a property of bones. Movement is a collaboration. It's a long conversation between the nervous system, the muscular system, and the skeletal system, all working together, all at once, all without you having to think about it. Let's start with the simplest version of a movement. You are lying in bed, and you decide to turn onto your side. That decision begins in the brain, in the outer layer of the brain called the motor cortex. A small group of nerve cells there becomes active, and it sends an electrical signal down through the spinal cord, along a nerve, and into the muscles of your trunk and shoulders. The signal arrives at the muscle, and the muscle responds by shortening, which pulls on a tendon, which pulls on a bone, and the bone moves. You have turned over. It happens in less than a second, and it involves millions of nerve cells and thousands of muscle fibers and dozens of bones, all coordinated without your attention. The only part you did was the wanting. The body did the rest. The muscles that move the skeleton are called skeletal muscles, and they're the most common type of muscle in the body. Skeletal muscle is a tissue made of long, thin cells called muscle fibers, and those fibers are packed with even smaller threads called myofibrils, and the myofibrils are made of two proteins called actin and myosin. These two proteins lie in overlapping rows, and when a nerve signal arrives, they slide past each other, which shortens the fiber, which shortens the muscle, which pulls the bone. That sliding is the basis of all movement. Every step you take, every breath you draw, every time you roll over in bed, it's actin and myosin sliding past each other in the dark, millions of tiny ratchets working in unison. And when the signal stops, the proteins slide back, the muscle relaxes, and the bone can move back. Muscles only pull, they never push. So for every movement of a bone in one direction, there is another muscle on the other side that pulls it back. The biceps pulls the forearm up. The triceps pulls it down. The quadriceps straightens the knee. The hamstrings bend it. The body is arranged in opposing pairs, pull and release, all day and all night. The place where a muscle attaches to a bone is usually a tendon. Tendons are tough, white, fibrous cords, made mostly of collagen, and they're extremely strong in tension. They don't stretch much, because their job is to transmit force from the muscle to the bone without losing any of it. The muscle belly is the soft, red, contractile part. The tendon is the white, glistening cable at each end. One end of the muscle attaches to a stable bone, and the other end attaches to the bone that moves. When the muscle shortens, it pulls on the moving bone, and the moving bone swings around a joint. The stable attachment is called the origin, and the moving attachment is called the insertion. For example, the biceps muscle originates on the scapula and inserts on the radius. When the biceps shortens, it pulls on the radius, and the forearm flexes at the elbow. The scapula stays put, the radius moves, and the elbow joint is the pivot. It's a lever system, and the body is full of them. Every joint is a fulcrum, every bone is a lever, every muscle is a force. And the arrangement is designed so that small contractions in the muscle produce large movements of the limbs. But not all bones are long levers. Some are flat shields, some are small blocks, some are irregular shapes, and each shape is matched to its job. The flat bones, like the bones of the skull and the ribs and the sternum and the pelvis, are broad and thin. They protect organs and provide large surfaces for muscle attachment. The long bones, like the femur and the humerus, and the bones of the forearm and leg, are levers for movement. The short bones, like the carpal and tarsal bones, are small and blocky, and they provide stability and shock absorption in the wrist and ankle. The irregular bones, like the vertebrae and the facial bones, have complex shapes that fit no simple category, and they protect and support and shape the body in ways that a simple cylinder or plate could not. The sesamoid bones, like the patella, are small bones embedded in tendons, and they improve leverage and protect the tendon from wear. And the sutural bones, sometimes called Wormian bones, are tiny extra bones that form within the sutures of the skull in some people. They're harmless variations, and they remind us that no two skeletons are exactly alike. The skeleton is a collection of shapes, and every shape has a reason. Now, if you are still awake, you might be wondering how all of this holds together. We have talked about bones and muscles and tendons, but what about the other connective tissues? What about ligaments and cartilage and fascia? These are the quiet tissues that bind the body together, and they deserve their own moment. Ligaments are tough bands of fibrous tissue that connect bone to bone. They are found at every joint, and their job is to hold the bones in alignment and to prevent excessive movement. They are slightly elastic, but not very, and if a joint is forced too far, the ligaments can tear. A sprain is an injury to a ligament. Tendons connect muscle to bone. A strain is an injury to a tendon or muscle. The two are often confused, but the difference matters because they heal differently. Ligaments have a poor blood supply and heal slowly. Tendons have a better supply, but still heal slower than muscle. Muscle has a rich blood supply and heals the fastest. Cartilage is another connective tissue, and it comes in several types. Hyaline cartilage is the smooth, glassy covering on the ends of bones in synovial joints. It's very low friction, and it allows the bones to glide over each other with almost no wear. Fibrocartilage is tougher and more fibrous, and it's found in the discs of the spine, the menisci of the knee, and the pubic symphysis. It resists compression and absorbs shock. Elastic cartilage is flexible and springy, and it's found in the external ear and the epiglottis. Cartilage has no blood supply of its own, so it relies on the fluid around it to bring in nutrients and remove waste. That's why cartilage damage heals so slowly, if at all. And fascia is the body's wrapping tissue. It's a sheet of connective tissue that surrounds every muscle, every bone, every nerve, and every organ. It holds everything in place, separates structures, and allows them to slide against each other as the body moves. Fascia is everywhere, and it's so pervasive that some people describe the body as a single continuous piece of connective tissue, shaped into bones and muscles and organs, all wrapped in fascia, all connected. It's a useful way to think about it. The body is not a bag of separate parts. It's a single, continuous fabric, folded and shaped into different structures, and the bones are the stiffened parts of that fabric, the places where the fabric has been reinforced with mineral until it can hold shape. So the skeleton and the muscles and the connective tissues are all part of one system, and that system is alive and responsive. It adapts to use. It strengthens under load. It heals when damaged. It changes over time. And it does all of this without your conscious direction. You are not the manager of your bones. You are the beneficiary of their quiet work. The best thing you can do for them is to move them sometimes, feed them reasonably, and let them rest. And tonight, the rest is being handled. The bones are unloaded. The discs are rehydrating. The muscles are going slack. The tendons and ligaments are settling into their resting lengths. The fascia is softening. The whole system is easing, layer by layer, into the quiet state of sleep. And if you are still listening, you might notice that your breathing has slowed. That's the respiratory system, and it works with the rib cage in a gentle rhythm, the ribs rising and falling, the sternum tilting, the thoracic spine flexing just slightly with every breath. You might notice your heartbeat if you pay attention, and that's the circulatory system, moving blood through the vessels that run through your bones, bringing nutrients to the osteocytes in their caves, carrying away the products of their work. You might notice the warmth of your own body, and that's the energy of metabolism, the slow burning of food and oxygen that keeps everything running at a steady temperature. All of these systems are working together, and the skeleton is part of all of it. The ribs are breathing. The marrow is making blood. The bones are storing minerals. The joints are resting in their capsules, lubricated by synovial fluid, waiting for the next movement, whenever that may be. So let the body be still now. Let the bones be heavy. Let the muscles be soft. Let the joints be loose. There is nothing to hold on to, nothing to solve, nothing to remember. The skeleton is doing its quiet work, and you are doing yours, which is simply to rest and let it happen. The bones have held you up all day. Now they can rest too, and so can you. The next part of the story will be here when you wake, or when you drift back to the surface for a moment, and it will continue in the same slow way, one idea at a time, until there are no more ideas left. But for now, there is only the dark, and the breath, and the slow, steady work of the body going on without you. Let's move now into the quieter side of the skeleton, the part that doesn't often get described. We have talked about the bones as levers, as protection, as a factory for blood, and as a storehouse for minerals. But there is another side to the skeleton, one that runs through all of those jobs and holds them together, and it has to do with how the bones talk to the rest of the body. The skeleton is not a silent frame. It sends and receives signals all the time. It listens to the blood, it responds to hormones, and it even sends messages back to the brain and other organs. For a long time, people thought of bone as a passive material, something that just sat there and held shape. But bone is an active participant in the body's ongoing conversation, and some of its messages are only now being understood. So let's sit with that idea for a while, because it's one of the most interesting things about the skeleton, and it's also one of the most calming. Even the hardest part of you is listening. The most obvious conversation the skeleton has is with the blood. Bone is constantly exchanging minerals with the bloodstream, and that exchange is regulated by hormones. The two main hormones are parathyroid hormone and calcitonin, and they work in opposite directions to keep the level of calcium in the blood within a narrow range. Calcium is essential for nerve signaling, for muscle contraction, for blood clotting, and for many other processes, and the body will not let the blood level drift far from its target. When the level drops, the parathyroid glands, 4 tiny glands in the neck, release parathyroid hormone. This hormone tells the osteoclasts to break down a little bit of bone and release calcium into the blood. It also tells the kidneys to hold on to calcium instead of letting it leave in the urine, and it activates vitamin D, which helps the gut absorb more calcium from food. When the blood calcium level rises too high, the thyroid gland releases calcitonin, which tells the osteoclasts to slow down, and the osteoblasts to take calcium out of the blood and deposit it in the bone. It's a feedback loop, and it runs all the time, adjusting the balance minute by minute. The skeleton is not just a static reservoir. It's a dynamic buffer, and it gives and takes calcium as the body needs it. The bones also respond to mechanical signals. This is a conversation between the skeleton and the forces of daily life. When you walk, run, lift, or even just stand, the bones experience mechanical load, and the osteocytes, the caretaker cells in their little caves, sense that load. They detect the bending and compression of the bone around them, and they respond by sending signals that recruit osteoblasts to build more bone in the loaded areas. This is why weight-bearing exercise strengthens bones and why bed rest and weightlessness weaken them. The bones are constantly asking, "Am I being used?" And the answer shapes their structure. An astronaut in space, floating without gravity, loses bone density because the answer to that question is no. A person who takes up running gains bone density in the legs because the answer is yes. The skeleton is always listening to the life you're living, and it adapts accordingly. This is not a conscious process, of course. It's a cellular conversation, carried out through chemical signals, and it happens without any awareness on your part. But it's happening. Right now, as you lie still, the osteocytes in your bones are sensing the gentle pressure of the mattress, and they are deciding, in their quiet cellular way, what to do about it. And the skeleton talks to the immune system too. This is one of the newer discoveries in bone biology, and it's still unfolding. Bone marrow, inside the bones, is not just a factory for blood cells, it's also a home for immune cells, and the bone itself helps to regulate them. The osteoblasts, the bone builders, produce substances that help maintain the population of stem cells in the marrow. The stem cells are the source of all blood cells, including the white blood cells that fight infection. So the health of the bones and the health of the immune system are linked. If the bones are unhealthy, the marrow is less effective, and the immune system can suffer. And conversely, some immune signals can affect bone remodeling. Inflammatory signals, for example, can stimulate osteoclasts and lead to bone loss. That's one of the reasons chronic inflammation is associated with weaker bones. The skeleton is not separate from the immune system, it's part of it, and the two systems influence each other in ways that are still being mapped. There is also a connection between the skeleton and the brain. Some researchers now talk about bone as an endocrine organ, meaning it secretes hormones into the blood. One of these is a protein called osteocalcin, which is produced by osteoblasts. Osteocalcin seems to have effects on energy metabolism, on insulin sensitivity, and possibly on brain function and mood. The details are still being worked out, and it's a young field, but the idea is striking. The bones are not just the recipients of signals from the brain and the glands. They send signals of their own, and some of those signals reach the brain. The skeleton, in some small way, participates in the chemistry of how you feel. The body is a circle, and every part touches every other part. That's a good thing to remember when you're trying to understand how any one part works. There is no isolated organ. There is no single system that acts alone. The bones are in the loop, and so is everything else. Let's turn now to the joints, because the joints are where the bones meet the outside world in a sense. They're the places where the skeleton allows movement, and they come in many forms. We have mentioned synovial joints, the big movable joints like the knee and the hip and the shoulder, but there are also fibrous joints, where the bones are joined by dense connective tissue and hardly move at all. The sutures of the skull are fibrous joints. The bones are interlocked and held tightly together, and in an adult they are essentially immobile. That's what protects the brain. The bones don't shift. In a newborn, the sutures are not yet fused, and the bones can move slightly, which allows the head to pass through the birth canal. But by adulthood, the sutures have closed, and the skull is a solid shell. There are also cartilaginous joints, where the bones are joined by cartilage and allow a little movement. The pubic symphysis is one example. The joints between the ribs and the sternum are another. These joints provide a small amount of give, which is enough to allow breathing and childbirth and shock absorption, but they are fundamentally stable. The body uses different types of joints for different purposes, and each type is a compromise between mobility and stability. The skull needs maximum stability and no mobility. The rib cage needs some mobility for breathing, but enough stability to protect the heart and lungs. The shoulder needs maximum mobility and accepts less stability. The hip needs maximum stability and accepts less mobility. Every joint in the body is a point on that spectrum, and the shape of the joint tells you where it sits. Inside a synovial joint, there is a small space filled with synovial fluid, and that fluid is one of the body's most elegant lubricants. Synovial fluid is produced by the synovial membrane, a thin layer of tissue that lines the inside of the joint capsule. The fluid is clear and slightly slippery, with the consistency of egg white, and it has two main jobs. It lubricates the joint, reducing friction between the cartilage surfaces, and it nourishes the cartilage, which has no blood supply of its own. The cartilage on the ends of the bones soaks up nutrients from the synovial fluid like a sponge, and it releases waste products back into the fluid, which is then cleared by the lymph system. When a joint moves, the fluid is squeezed and spread across the cartilage surfaces, and that movement is what keeps the cartilage healthy. A joint that is immobilized for a long time becomes stiff, and the cartilage can thin, because it's not getting the regular compression and release that brings it nutrients. That's why movement is so important for joint health. It's not just about keeping the muscles strong, it's about feeding the cartilage. A gentle walk, a slow stretch, a careful range of motion, these things literally feed the joints. And when you rest at night, the joints are resting too, the synovial fluid pooling around the cartilage, the membranes quiet, the whole system waiting for the next movement to squeeze and nourish it again. The cartilage itself is a remarkable material. It's smooth and slightly springy, and it's much lower in friction than any artificial surface. In a healthy joint, the two cartilage surfaces slide over each other with almost no resistance, and they can do so for decades without wearing out. The structure of cartilage is different from bone. It's mostly water held in a mesh of collagen and large molecules called proteoglycans, which give it its springiness. When the joint is loaded, the water is squeezed out of the cartilage and into the synovial fluid, and when the load is removed, the water is drawn back in. It's a bit like squeezing a wet sponge and letting it expand again. This constant ebb and flow of water is what keeps the cartilage nourished and healthy. And because cartilage is smooth and wet, it allows the bones to glide. It's the living bearing surface of the body, and it's better than anything we have been able to make. The joint capsule and the ligaments around a synovial joint provide the stability that the cartilage alone cannot. The capsule is a tough, fibrous sleeve that encloses the joint, and it's reinforced by thickenings in places, which are the ligaments. Inside the capsule, the synovial membrane produces the fluid, and outside, the muscles and tendons cross the joint and provide dynamic support. The whole arrangement is layered, and each layer has a job. The bones provide the shape. The cartilage provides the glide. The fluid provides the lubrication and nutrition. The capsule and ligaments provide the passive restraint. The muscles and tendons provide the active control, and the nerves in and around the joint provide the feedback, telling the brain where the joint is and how it's moving. This is called proprioception, the sense of your own body in space. You don't have to look at your arm to know where it is. You can feel it, even with your eyes closed. That feeling comes from receptors in the joints and muscles and skin, all sending signals to the brain, which builds a model of your body's position. Proprioception is what allows you to walk in the dark, to touch your nose with your finger, to roll over in bed without falling out. And the bones and joints are a big part of it. They're not just passive levers, they're sense organs too. So the skeleton in every part is talking to the blood, to the muscles, to the brain, to the immune system, to the forces of gravity and movement. It is not a dead frame. It is a living, sensing, responding part of the body, and it is deeply connected to everything else. When you lie in bed at night, your bones are not just lying there. They are exchanging signals with the blood, adjusting mineral levels, sensing the weight of the mattress, responding to the hormones in your bloodstream, slowly remodeling, slowly adapting, slowly continuing the long, quiet conversation that has been going on since before you were born. And you don't have to listen, you don't have to respond. The conversation takes care of itself, and your only part in it is to rest and let it happen. So let the body soften further. Let the joints loosen. Let the cartilage soak in its fluid. Let the osteocytes settle in their caves. Let the bones grow heavy and still. The conversation is not urgent. It is not loud. It is the quietest, most patient conversation in the body, and it will continue all through the night, whether you are awake to hear it or not. There is nothing to hold, nothing to fix, nothing to understand. There is only the dark and the breath and the slow, steady work of the living skeleton going on without you. There is a kind of map that runs through the body, and we have been tracing parts of it for a while now. It is not a map of roads or rivers, but a map of levers and pivots, of struts and shields, of cables and cushions. Every bone we have named is a landmark on that map, and every joint is a crossroads. And like any map, it is easier to hold in the mind if you can see it from above, as a whole, rather than piece by piece. So let's do that now. Let's step back from the details and look at the skeleton as one continuous structure, from the crown of the head to the soles of the feet, and see how the parts repeat and vary and connect. Because the more you look at it, the more you see that the body is built from a small number of simple ideas, repeated and adapted. Long bones, flat bones, short bones, irregular bones, hinge joints, ball and socket joints, pivot joints, gliding joints, levers, shields, springs, and all of them made from the same living material, shaped by the same quiet processes, maintained by the same slow conversation with the rest of the body. Consider the long bones, the femur and the humerus, the tibia and the radius, the ulna and the fibula, the metacarpals and the metatarsals, the phalanges of the fingers and toes. They all share the same basic plan, a long shaft called the diaphysis, which is mostly compact bone and is built for strength and leverage. Two wider ends, called the epiphyses, which are mostly spongy bone covered with a thin shell of compact bone and which form the joint surfaces. A growth plate between the shaft and each end during childhood, which is where the bone grows longer. A marrow cavity inside the shaft, filled with yellow marrow in adults. A covering of periosteum on the outside, and a lining of endosteum on the inside. A blood supply that enters through a nutrient foramen and branches through the bone. The same plan, repeated in every long bone in the body and adapted in each place to the particular demands of that part. The femur is huge and heavy because it carries the weight of the body. The humerus is lighter because it's used for reaching and lifting, not for bearing the whole body. The metacarpals are small because the hand needs fine control, not brute strength. But underneath the differences, the plan is the same. A long bone is a long bone, whether it's the length of your thigh or the length of your little finger. Consider the short bones, the carpals of the wrist and the tarsals of the ankle. They're small and blocky, with a thin shell of compact bone around a core of spongy bone. They don't have long shafts or growth plates like the long bones, because they don't need to be long. They need to be stable, to transfer force from one set of bones to another, and to allow a little movement in many directions. The wrist and the ankle are both made of clusters of short bones, and those clusters allow the hand and the foot to flex and extend and tilt and glide. The short bones are the body's ball bearings, the small, hard pieces that allow complex movement in a small space. And again, the plan is repeated. A carpal bone and a tarsal bone are built on the same plan, adapted to the different demands of the hand and the foot. The hand needs more mobility, the foot needs more stability, but the basic unit is the same. Consider the flat bones. The skull, the sternum, the ribs, the scapulae, the pelvis. They're broad and thin, with a layer of spongy bone sandwiched between two layers of compact bone. They don't act as levers, they act as shields, protecting the organs beneath them and providing large surfaces for muscle attachment. The skull protects the brain, the ribs and sternum protect the heart and lungs, the pelvis protects the lower organs, the scapulae protect the back of the chest and anchor the shoulder. The flat bones are the body's armor, and they're built for coverage rather than leverage. But they also contain marrow, and they're important sites of blood cell production. The flat bones of the pelvis and sternum are among the most active marrow sites in the adult body, and they're still making blood cells every day of your life. So the shields are also factories, and the same plan serves both purposes. Consider the irregular bones, the vertebrae, the facial bones, the bones of the middle ear. They have complex shapes that don't fit into the simple categories. They're not long, not short, not flat. They're shaped by their particular jobs, and their shapes are often intricate. The vertebrae are shaped like rings with projections, because they have to protect the spinal cord, bear weight, and anchor muscles all at once. The facial bones are shaped around the eyes and nose and mouth, forming the cavities and passages of the face. The bones of the middle ear are shaped like tiny levers because they carry sound vibrations from the eardrum to the inner ear. The irregular bones remind us that the body is not built from a kit of standard parts. It's built by adaptation, each bone shaped by the forces and functions it serves. And yet, even the irregular bones are made of the same materials, the same collagen and mineral, the same osteons and osteocytes, the same living tissue. And consider the joints. We have named the types, but look at them now as a family. The hinge joints, the elbow and the knee and the ankle, and the joints of the fingers and toes. They allow movement in one plane, like a door. The ball and socket joints, the hip and the shoulder. They allow movement in many planes, like a joystick. The pivot joints, the joint between the atlas and the axis, and the joint between the radius and the ulna. They allow rotation, like a wheel. The gliding joints, the joints between the carpal bones and the tarsal bones. They allow small sliding movements, like a stack of plates shifting. The saddle joints, the joint at the base of the thumb. They allow movement in two planes, like a rider in a saddle. The condyloid joints, the joints at the knuckles. They allow bending and straightening plus a little side to side. Every movable joint in the body is one of these types, or a combination of them, and every type is a solution to the same problem: how to let two bones move relative to each other without falling apart. The body has solved that problem in several different ways, and it uses each solution where it fits best. Now, if you could see the whole skeleton at once, you would notice something else. You would notice the symmetry. The body has two sides, left and right, and the skeleton is almost perfectly mirrored. Two arms, two legs, two shoulder blades, two hip bones, two sides of the skull, two sides of the rib cage. Even the spine, which is a single midline structure, is made of paired parts, the two transverse processes, the two facet joints, the two sides of the vertebral arch. The symmetry is not perfect, of course. Most people are slightly asymmetric in small ways. One leg a little longer, one shoulder a little higher, one side of the face a little different from the other, but the basic plan is bilateral symmetry, and it goes back a long way in the history of life. A body with two mirror image sides is well suited to moving forward through the world, to reaching and grasping and walking, and the skeleton reflects that. It's a balanced structure, and balance is one of its deepest principles. The body is always working to stay balanced, to distribute forces evenly, to keep the left and right sides working together. When you stand, the weight is shared between your two legs. When you walk, the load shifts from one side to the other in a steady rhythm. When you breathe, the rib cage expands symmetrically. The symmetry of the skeleton is not just a fact of anatomy, it's a condition of movement. It's what makes walking and running and reaching possible. And yet the symmetry is not rigid. The body is also capable of asymmetry when the task demands it. The heart sits more to the left. The liver sits more to the right. The right lung has 3 lobes, the left has 2. The dominant hand is stronger and more skilled than the other. The body is not a machine stamped out of identical halves. It's a living organism, and it adapts, and the skeleton adapts with it. A tennis player develops denser bone in the playing arm. A seamstress develops finer control in the dominant hand. The body is always shaping itself to the life you live, and the skeleton is part of that shaping. It's not a fixed frame, it's a responsive frame, and it changes. This is a good place to pause and remember where we started. The first thing we said, all the way back at the beginning, was that the body is organized in nested layers. Cells make tissues, tissues make organs, organs make systems, systems make the body, and the skeleton is a perfect example of that layering. Bone cells make bone tissue makes each bone, and each bone is an organ. The bones together make the skeletal system, and the skeletal system works with the other systems to make the body. It's a hierarchy of organization, and it runs all the way from the tiny osteocyte in its cave to the whole skeleton, and from the whole skeleton to the whole body, and from the whole body to the person lying in bed, listening or not listening, or half asleep. Every layer is alive, every layer is connected, every layer is doing its quiet work, and none of it requires your attention. That's the deepest comfort of anatomy, I think. The body is not a problem you have to solve. It's a process you get to inhabit. You don't have to manage it. You don't have to understand it. You can just let it be, and it will carry you through the night. So as we come toward the end of this slow walk through the skeleton, let's gather the threads one more time, gently, without pulling too hard. The skeleton is the frame. It holds you up, it protects the soft parts, it works with the muscles to move you, it makes your blood, it stores your minerals, it talks to the rest of the body in quiet chemical and mechanical voices, it adapts to use, it heals when broken, it changes over time. It is made of living cells in a hard matrix, and those cells never stop working. The bones are not dead, they are not dry, they are not silent, they are a living system, and they are part of the living system that is you. And when you sleep, they sleep with you, in their way. The osteoclasts slow their work. The osteoblasts rest. The osteocytes sit in their caves, feeling the stillness. The marrow keeps making blood, because it never stops. The joints settle into their capsules. The discs rehydrate. The whole structure eases, and the body lets go. There is one last thing to say, and it's the thing that has been underneath all of this from the beginning. You don't need to remember any of it. You don't need to know the names of the bones or the types of joints or the cells that build and break and rebuild. You don't need to hold any of this in your head. The body already knows it. The body has known it since the first cells began to divide, and it will know it long after you have stopped thinking about it. The skeleton is not asking you to understand it. It's only asking you to let it do its work. So let it. Let the skull be heavy on the pillow. Let the spine soften into the bed. Let the ribs rise and fall with the breath. Let the pelvis settle and the legs grow still. Let the bones rest, and let yourself rest with them. The morning will come when it comes, and the skeleton will be ready for it, and so will you. But for now, there is nothing to do. There is only the dark and the quiet, and the slow, patient work of the body, going on without you and with you all at once. We have reached the last part of this slow walk, and it can be the softest one. There is no new territory to cover now, no new names to learn, no new systems to trace. Everything we have talked about is already in place, and it has been in place all along, working quietly while the words went by. The last section of a long, slow story is not the place for new facts, it's the place for letting go. And that's what this is for. Letting go of the names, the shapes, the lists. Letting the body be a body again, not a map, not a diagram, not a thing to understand, but a warm, breathing, resting body, with the lights low and the work of the day already done. If you are still awake, then perhaps you are one of the ones who listens all the way to the end. And if you are, then you can use these last minutes as a kind of settling, a quiet settling of everything that has been said. We began with the smallest unit, the cell, and we said that cells make tissues, tissues make organs, organs make systems, systems make the body. And then we walked through the skeletal system, from the skull to the spine, from the ribs to the pelvis, from the arms to the legs, from the joints to the living bone itself. And through all of it, the same ideas kept returning. The body is organized. The body is alive. The body takes care of itself. The body does not need you to manage it. The body needs you to rest. And so the bones are resting now, as much as bones ever rest. The skull is heavy against the pillow, and the small bones of the inner ear are still, and the tiny muscles that move them are loose. The jaw is slack, the teeth not quite touching, the tongue resting on the floor of the mouth. The spine is long and soft against the bed, the vertebrae no longer holding the full weight of the body, the discs slowly filling with fluid again after the long compression of the day. The ribs are moving with the breath, but the breath is slower now, and the ribs are barely lifting. The sternum is quiet over the heart, and the heart is beating its slow, steady rhythm, not because you're telling it to, but because it has always known how. The shoulders are soft, the scapulae settling against the mattress, the clavicles resting in their long, gentle curves. The arms are heavy, the humerus and the radius and the ulna lying still, the carpals and metacarpals and phalanges loose and open. The pelvis is a bowl of stillness, the ilia and ischia and pubic bones cradling the soft organs below. The femurs are long and quiet, the kneecaps resting in their grooves, the tibias and fibulas side by side, the ankles slack, the feet turned out or drawn up, the tarsals and metatarsals and phalanges no longer carrying anything at all. And inside all of those bones, the cells are working. The osteocytes are sitting in their lacunae, sensing the stillness, and they are not alarmed by it. The osteoblasts and osteoclasts are moving at their usual slow pace, building and breaking and rebuilding, because that's what they do, whether you're awake or asleep, whether you're running or lying still. The marrow is making red blood cells and white blood cells and platelets and sending them out into the bloodstream, where they travel through arteries and veins that pass through the very bones that made them. The periosteum is quiet over the surface of each bone, and the endosteum is quiet within, and the synovial fluid is pooled in every joint, feeding the cartilage, lubricating the surfaces, waiting for the next movement, whenever that may be. The whole skeleton is alive, and it is resting, and it is taking care of itself, and it is taking care of you. And you, the person who is lying there, you are not the skeleton, and you are not the brain, and you are not the breath. You are the whole of it, and you are also something else, something that can notice it and then let it go. That's the strange and gentle thing about being alive. You can watch yourself from the inside, and then you can stop watching. You can be aware of the breath, and then you can forget the breath, and the breath goes on. You can be aware of the body, and then you can forget the body, and the body goes on. And eventually, when sleep comes, you are not aware of anything at all, and still everything goes on. That is the deep trust that underpins all of it. The trust that the body will keep doing what it does, without your help, while you are gone from yourself for a while. And that trust is well placed. The body has never once let you down. It has been breathing and beating and digesting and repairing and rebuilding since before you knew what any of those words meant. It will do it tonight. It will do it tomorrow. It will do it for as long as it can. So there is nothing left to hold. Not the names of the bones, not the types of joints, not the layers of the body, not the idea of cells and tissues and organs and systems. Those were just words, and they have done their work. They gave your mind something slow and steady to rest on, while the rest of you let go. And if you remember them tomorrow, that's fine. And if you don't, that's also fine. The body doesn't need you to remember, it only needs you to rest. And if you have been drifting in and out, catching only pieces, then those pieces were enough. You didn't miss anything. There was no test at the end, no thread you had to follow. It was always just a long, soft walk, and you were welcome to fall asleep at any point along the way. That was the point. If you'd like to revisit any of this while you're awake, the No Fluff Anatomy and Physiology Guide is in the description, and it covers the same ground in a form you can actually read. And if you prefer to learn properly, while awake and alert, the No Fluff Academy channel has structured lessons on the same subjects. But neither of those things needs to be thought about now. They will still be there tomorrow, if you want them. They are not going anywhere. Nothing is going anywhere. The night is not going anywhere. The bed is not going anywhere. The quiet is not going anywhere. So let this be the ending, or not an ending, but a gentle stopping point. The words can wind down now, and you can let them fade. There is nothing else you need to do. There is nowhere else you need to be. The body is lying in the dark, and the bones are holding their shape, and the blood is moving slowly through the vessels, and the breath is coming and going, and the mind is softening at the edges, and sleep is somewhere nearby, not hurrying, not waiting, just nearby. It will come when it comes, and until then, you can lie here in the warm quiet, and let the body do what it does, and let the words fall away, And let the last thought be the simplest one. The body is taking care of you. It always has. It always will. And all you have to do is rest.